Gravity is often introduced as a force that pulls objects toward one another, but at a deeper level, it is more accurately described as a vector field that fills space. At every point in space, gravity assigns both a direction and a magnitude, indicating how a freely moving test particle would accelerate if placed there. Near Earth's surface, this field appears almost uniform. The direction is downward, and the magnitude changes so slowly with height that, over human scales, it can be treated as constant. This apparent simplicity hides a crucial fact. Gravity is never truly uniform. Its strength and direction always vary from point to point, even if those variations are extremely small. It is this spatial variation, not gravity itself, that gives rise to tidal forces. To understand why this matters, it helps to imagine an idealized point mass. A point mass has no spatial extent. It occupies a single location in space, so the gravitational field acting on it is sampled at only one point. The entire mass accelerates uniformly according to the local value of the gravitational field. There is no internal structure to deform, no separation between different parts of the object, and therefore no internal stress generated by gravity alone. In classical mechanics, this is why point particles are so convenient. Gravity causes them to accelerate, but it cannot stretch or compress them because there is nothing to stretch or compress. Extended bodies are fundamentally different. Any real object occupies a finite volume of space, which means different parts of it sample slightly different values of the gravitational field. Even in a weak field like Earth's, the gravitational acceleration at your feet is marginally stronger than at your head, simply because your feet are closer to Earth's centre. The difference is tiny, far too small to notice in daily life, but it is not zero. That difference is the essence of a tidal force. Tidal forces arise because gravity varies across the size of an object, producing differential acceleration between its parts. This distinction between uniform acceleration and differential acceleration is critical. A uniform gravitational field causes all parts of an object to accelerate together. A spatially varying gravitational field causes different parts to accelerate by different amounts. The first produces motion, the second produces deformation. Tidal forces are therefore not an additional kind of gravity layered on top of ordinary gravity. They are the manifestation of gravity's non-uniformity. Mathematically, this can be made precise by expanding the gravitational field around some reference point. The value of the field itself represents the first-order effect, the overall acceleration of the object's center of mass. The spatial derivatives of the field represent second-order effects, how that acceleration changes from point to point. These derivatives determine how nearby particles move relative to one another. In Newtonian gravity, the gravitational field is derived from a potential, and the second derivatives of that potential encode the tidal field. In more advanced language, this is the tidal tensor, but the physical meaning remains simple. Tides measure how gravity changes across space. If the gravitational field were perfectly uniform, all first-order effects would remain, but all second-order effects would vanish. Objects would fall, orbit, or drift, but they would never be stretched, squeezed, or torn apart by gravity alone. In reality, no gravitational field is perfectly uniform, because gravity originates from masses that occupy finite regions of space. As a result, tidal forces are universal. They exist wherever gravity exists, even if their effects are often negligible. The magnitude of tidal acceleration depends directly on the size of the object experiencing it. Consider 2 points separated by a small distance within an extended body. Each point experiences a slightly different gravitational acceleration. The difference between those accelerations is proportional to the separation distance. This linear dependence is a defining feature of tidal forces. Double the size of the object, and the differential acceleration across it doubles as well, assuming the same background gravitational field. This is why small objects can survive environments that would tear larger objects apart. A grain of dust and a mountain experience the same gravitational field at their centres of mass, but the mountain spans a much larger range of gravitational values and therefore experiences far stronger internal stresses. This scaling has profound consequences. It means that tidal forces are sensitive not only to where an object is, but to what it is. Size matters, shape matters, and internal structure matters. A compact, rigid object can withstand tidal gradients that would shred a loosely bound or extended one. Conversely, even a strong object can be destroyed if the tidal gradient becomes large enough across its dimensions. The directionality of tidal forces is equally important. In a spherically symmetric gravitational field, such as that produced by an isolated star or planet, tidal forces stretch objects along the radial direction and compress them along directions perpendicular to it. This pattern arises directly from the geometry of the gravitational field. Gravity points inward toward the mass generating the field, and its strength increases as one moves closer to that mass. The part of an object closer to the source is pulled more strongly than the part farther away, producing stretching along the line connecting the object to the source. At the same time, gravity has a converging geometry. Field lines that point toward the center of mass get closer together as they approach it. This convergence produces lateral compression. Points within an object that are side by side experience accelerations that point slightly toward one another, squeezing the object in directions perpendicular to the radial axis. The result is a characteristic tidal deformation, elongation in one direction and compression in the others. This stretching compression pattern is not a matter of analogy or metaphor. It is a direct consequence of how gravitational fields behave in three-dimensional space. In Newtonian gravity, it follows from the inverse square law. In general relativity, it follows from the curvature of spacetime itself. Either way, the qualitative behavior is the same. Tides pull things apart in one direction, while squeezing them in others. An important and often misunderstood point is that freefall does not eliminate tidal forces. It is true that an observer in freefall feels weightless. A freely falling elevator, for example, provides an environment in which local gravitational forces appear to vanish. Objects float, and there is no sensation of being pulled downward. This can create the impression that gravity has somehow been turned off. In reality, only the first-order effect of gravity has been removed. The observer and everything nearby are accelerating together under the influence of the gravitational field. The second-order effects remain. Even in freefall, different parts of an extended object still experience slightly different gravitational accelerations. These differences do not disappear simply because the object is falling. They are intrinsic to the spatial structure of the field. In a small enough region of space, tidal effects can be made arbitrarily small, which is why local inertial frames are so useful in physics, but they can never be eliminated entirely over finite distances. This is why astronauts orbiting Earth experience weightlessness, but not immunity to tides. The Moon continues to raise tides in Earth's oceans even though the Earth-Moon system is in continuous freefall around the Sun. Similarly, a spacecraft falling toward a black hole does not escape tidal forces simply by falling freely. If the spacecraft is small and the tidal gradients are weak, the effects may be negligible. If the gradients are strong, the spacecraft will be stretched and compressed regardless of its state of motion. The persistence of tidal forces in freefall reveals something deep about gravity. Gravity is not just an acceleration, it is a geometric property of space, or in relativistic terms, of spacetime. Freefall removes the sensation of force, but it does not flatten the geometry. Curvature remains, and curvature is what produces tides. The strength of tidal forces increases rapidly as one approaches a massive object. In Newtonian gravity, the gravitational acceleration due to a point mass decreases with the square of the distance. Tidal forces, however, depend on how quickly that acceleration changes with distance. This introduces an additional factor of distance in the denominator. As a result, tidal acceleration scales inversely with the cube of the distance to the mass. This inverse cube scaling is one of the most important quantitative features of tidal physics. It explains why tides become dominant in extreme gravitational environments. Halving the distance to a mass increases the tidal force by a factor of 8. Reducing the distance by a factor of 10 increases the tidal force by a factor of 1,000. This rapid growth means that tidal effects are often negligible, far from massive objects, but overwhelming close to them. The inverse cube law also explains why massive objects are not automatically more dangerous tidally. A very massive object produces strong gravity, but if its mass is spread over a large volume, the gravitational gradient near its surface can be modest. Conversely, a smaller but more compact object can produce extreme tidal gradients. What matters is not just mass, but how concentrated that mass is. This distinction becomes especially important when considering compact astrophysical objects. Near ordinary planets and stars, tidal forces are usually weak enough that only very large, loosely bound systems, such as oceans or extended atmospheres, respond noticeably. Near dense objects like white dwarfs, neutron stars and black holes, the same inverse cube scaling drives tidal forces to extraordinary levels over relatively small distances. The proportionality of tidal acceleration to both object size and inverse cube distance sets up a competition between internal cohesion and external gravitational gradients. Every object has mechanisms that hold it together. Chemical bonds, material strength, self-gravity, or in extreme cases, nuclear forces. Tidal forces act to pull different parts of the object apart, or push them together in conflicting directions. When the tidal stresses exceed the object's internal binding forces, structural failure begins. This failure does not occur instantaneously. It starts with small deformations, stretching and compression that may be elastic or plastic depending on the material. As the tidal gradient increases, these deformations grow. Cracks form, bonds break, and eventually the object can no longer maintain its integrity. In the most extreme environments, the time scale for this process can become extremely short, approaching the dynamical time scale of the object itself. What makes tidal forces particularly unforgiving is that they act continuously and deterministically. There is no shielding against them. Unlike radiation, which can sometimes be blocked or absorbed, tidal forces arise from the geometry of the gravitational field itself. Any extended object within that field is subject to them, regardless of its composition. At a fundamental level, tidal forces are a measure of how gravity distinguishes between nearby points in space. They are the reason gravity can shape structures rather than merely move them. They explain why moons become tidally locked, why rings form around planets, why stars can be torn apart near galactic centers, and why matter near compact objects can be stretched into long, thin streams. In the most extreme cases, tidal stretching becomes so severe that the object's length along the radial direction grows dramatically while its cross-section shrinks. This process, informally known as spaghettification, is not a separate phenomenon from tides. It is simply the extreme limit of the same differential gravity that operates everywhere in the universe, pushed to an intensity where familiar notions of structure and cohesion fail. At this stage, nothing qualitatively new has been introduced. The same principles that cause Earth's oceans to bulge under the moon's influence also govern the fate of matter near a black hole. The difference lies entirely in scale. Stronger gravitational gradients, larger objects, and closer proximity to massive bodies push tidal effects from the imperceptible into the catastrophic. By understanding gravity as a spatially varying vector field, by recognizing the distinction between uniform acceleration and differential acceleration, and by appreciating the inverse cube scaling that governs tidal strength, the foundations of tidal forces become clear. Everything that follows, from gentle ocean tides to the violent stretching of stars and planets, is a consequence of these basic principles acting under different conditions. The physics of tides is often first encountered through the familiar rhythm of rising and falling oceans on Earth. This setting provides a concrete and mathematically clean baseline from which the full generality of tidal phenomena can be understood. The same principles that lift seawater along coastlines also operate in stars, planets, and galaxies, differing only in scale, material response, and timescale. By carefully examining the Earth-Moon-Sun system, the essential ingredients of tidal physics become visible in a form that can be extended without modification of the underlying laws to the most extreme environments in the universe. At its core, the Earth-Moon tidal system is a three-body gravitational interaction in which spatial variations in gravity dominate the observable effects. The Moon exerts a gravitational pull on Earth that is stronger on the near side than on the far side. This differential pull produces two tidal bulges, one facing the Moon and one on the opposite side. The existence of the far side bulge is often counterintuitive, but it arises naturally from the fact that Earth as a whole is accelerated toward the Moon, while the far side water lags slightly behind, creating a relative outward displacement. The Sun also contributes to Earth's tides, though its much greater distance weakens its tidal influence despite its far larger mass. Quantitatively, lunar tides dominate solar tides by roughly a factor of 2, a direct consequence of the inverse cube dependence of tidal strength on distance. The geometry of these tidal bulges is not static. If Earth were perfectly fluid, frictionless, and non-rotating relative to the Moon, the bulges would align exactly along the Earth-Moon axis. In reality, Earth rotates once every 24 hours, while the Moon orbits Earth roughly once every 27.3 days. This mismatch in angular velocities introduces a dynamical effect known as tidal lag. Earth's oceans possess viscosity, interact with coastlines, and experience friction with the ocean floor. As a result, the tidal bulges are carried slightly ahead of the Earth-Moon line by Earth's rotation. This angular offset is small in absolute terms, but its consequences are profound. Because the bulges are no longer perfectly aligned with the Moon, they exert a gravitational torque on it. The near-side bulge pulls the Moon forward along its orbit, transferring angular momentum from Earth's rotation to the Moon's orbital motion. This process causes Earth's rotation to slow gradually and the Moon's orbit to expand. Laser-ranging experiments, using reflectors left on the Moon's surface, measure the Moon's recession at about 3.8 centimeters per year, or roughly 1.5 inches per year. At the same time, Earth's day lengthens by a few milliseconds per century. This exchange of angular momentum is inseparable from energy dissipation. Tidal deformation is not perfectly elastic. As Earth's oceans and solid body are repeatedly distorted, mechanical energy is converted into heat through friction and internal damping. This energy dissipation is why tides are not reversible. Over geological timescales, it has altered Earth's rotation rate, the Moon's distance, and even Earth's climate history by influencing day length and seasonal cycles. Tidal dissipation represents a pathway by which gravitational interactions irreversibly reshape planetary systems. The same framework applies when the Sun is included. Solar tides interact with lunar tides in a process known as tidal superposition. When the Sun, Earth, and Moon align during new and full moons, their tidal effects reinforce one another, producing spring tides with larger amplitude. When the Sun and Moon are at right angles relative to Earth, their tidal effects partially cancel, producing neap tides. These patterns emerge directly from linearity in the tidal response. Tidal accelerations add vectorially, and the resulting deformation reflects the combined gravitational gradients. What makes this terrestrial example so powerful is that the governing equations are scale-free in form. The tidal acceleration across an object depends on three parameters: the mass of the perturbing body, the distance to that body, and the size of the object experiencing the tide. Specifically, tidal acceleration scales linearly with object size and inversely with the cube of the distance. Nothing in this relationship restricts it to oceans, planets, or even fluids. Replace Earth with a star, the Moon with a black hole, and the ocean with stellar plasma, and the same mathematics applies. Scaling from meters to stellar radii simply changes the numerical values involved, not the structure of the physics. An ocean tide on Earth involves height differences measured in meters and timescales of hours. A tidal deformation of a star involves length scales of hundreds of thousands of kilometers and timescales of minutes to hours, depending on orbital parameters. In both cases, the deformation reflects a balance between external tidal stress and internal restoring forces. At small scales, material strength plays a dominant role in determining tidal response. Rocks, metals, and ice possess tensile and compressive strengths that resist deformation. On Earth, the solid body tide, the deformation of Earth's crust under lunar gravity, has an amplitude of only about 30 centimeters, or roughly 1 foot, far smaller than ocean tides. The rigidity of rocks suppresses tidal deformation, storing much of the energy elastically rather than dissipating it. As objects grow larger, however, self-gravity increasingly overwhelms material strength. A mountain-sized object resists deformation primarily through the strength of its constituent materials. A planet-sized object resists deformation primarily through its own gravity, which acts to restore spherical symmetry. This transition explains why planets behave like fluids over long timescales despite being made of solid rock. Given enough time, rock flows. Under sustained tidal stress, even the strongest materials yield. This distinction becomes critical in astrophysical systems. Small asteroids passing near a planet may survive intact if their internal cohesion exceeds the tidal stress. Larger rubble pile asteroids, held together primarily by weak self-gravity, can be torn apart well outside a planet's surface. At stellar scales, material strength becomes irrelevant. Plasma has essentially no shear strength, and stellar structure is governed entirely by pressure gradients, gravity, and thermal processes. Tidal forces can therefore reshape stars dramatically, producing elongation, compression, and ultimately disruption. The Earth-Moon system also illustrates the importance of time scale. Tidal deformation does not occur instantaneously. It depends on how quickly an object can respond to changing gravitational conditions. If the tidal forcing varies slowly compared to the object's internal dynamical timescale, the response is quasi-static. If the forcing varies rapidly, inertial effects dominate, leading to oscillations, resonances, or shocks. On Earth, the tidal forcing frequency is low compared to the timescale on which oceans can flow, allowing large-scale redistribution of water. In stars, tidal forcing during close encounters can occur on time scales comparable to or shorter than the star's sound-crossing time. In such cases, tides can excite global oscillation modes, generate shocks, and deposit energy deep within the stellar interior. The same equations describe both situations, but the physical outcomes differ because the internal response differs. This highlights a key limitation of analogies. While ocean tides provide an accessible entry point into tidal physics, they are not perfect models for all tidal phenomena. Oceans are thin surface layers on a rotating, rigid body. Stars are fully three-dimensional, compressible fluids with nuclear energy sources. Planets may have layered interiors with vastly different viscosities and thermal properties. Galaxies consist of collisionless stellar populations and dark matter halos, responding to tides through orbital dynamics rather than material deformation. Despite these differences, certain analogies remain robust. The concept of tidal locking, for example, extends cleanly from the Moon to exoplanets and stars in close binaries. Tidal dissipation tends to synchronize rotation with orbital motion, minimize energy for fixed angular momentum, and drive systems toward stable configurations. Many exoplanets are expected to be tidally locked to their host stars, just as the moon is locked to Earth, presenting the same face at all times. Other analogies fail if pushed too far. The idea of a single, well-defined tidal bulge becomes misleading in highly dynamical or relativistic systems. Near compact objects, tidal deformation may be so rapid and non-linear that no steady bulge forms. Instead, matter can be stretched into streams, compressed violently, or shock-heated beyond recognition. In such regimes, the ocean tide picture breaks down, and one must return to first principles. Another limitation arises from rotation. Earth's tides are strongly influenced by its rotation rate, which sets the Coriolis force and shapes ocean currents. In many astrophysical systems, rotation may be negligible, dominant, or relativistic. Rapid rotation can stabilize objects against tidal disruption by redistributing mass and altering effective gravity. Slow rotation may enhance tidal effects by allowing greater deformation. These subtleties have no direct terrestrial analogue. Nevertheless, the Earth-Moon-Sun system remains invaluable precisely because it exposes the essential mechanisms without extreme conditions. It demonstrates how tidal forces arise from differential gravity, how they produce deformation rather than net motion, how they transfer angular momentum, and how they dissipate energy irreversibly. These processes operate continuously, reshaping systems over time. When extended to cosmic scales, tidal forces become architects of structure. In stellar systems, they circularize orbits, synchronize rotations, and drive mass transfer. In galaxies, they strip stars from satellites, forming elongated stellar streams that trace gravitational potentials. In galaxy clusters, they distort and disrupt entire galaxies, redistributing matter over hundreds of thousands of light years. The same inverse cube law that governs the rise and fall of Earth's oceans governs these phenomena, differing only in magnitude and context. The continuity between ocean tides and cosmic tides underscores a central theme of gravitational physics. Scale changes outcomes, but not laws. By understanding tides in the most familiar setting, it becomes possible to recognize their signatures everywhere else. The ocean's slow pulse under lunar gravity is not an isolated curiosity. It is a low-energy expression of a universal process that, under different conditions, can stretch stars, heat planets, and ultimately tear matter apart. In this sense, tides serve as a bridge between the everyday and the extreme. They reveal how gravity, acting not just as a pull, but as a spatially varying field, shapes systems across the universe. From the quiet deformation of Earth's oceans to the violent disruption of stars near galactic centers, the physics remains continuous. What changes is only the scale at which differential gravity asserts itself, and the ability of matter to resist or accommodate the stress imposed upon it. In Newtonian gravity, tidal forces can be described without abandoning the idea of gravity as a force acting at a distance. The gravitational field assigns an acceleration vector to every point in space, and tidal effects arise from how that vector changes from point to point. If two nearby particles are separated by a small distance, the difference in the gravitational acceleration they experience determines how their separation evolves over time. This description is sufficient for many practical purposes, but it hides a deeper structure that becomes unavoidable when gravity is treated relativistically. In general relativity, tides are no longer a secondary effect derived from a force field. They are the most direct and physically meaningful manifestation of gravity itself. The Newtonian approach begins with the gravitational potential, a scalar function whose gradient gives the gravitational acceleration. By taking second spatial derivatives of this potential, one obtains a mathematical object known as the tidal matrix. Each component of this matrix describes how one component of gravitational acceleration changes with position in a given direction. Physically, the tidal matrix encodes how neighbouring trajectories diverge or converge due to gravity. It predicts stretching along some axes and compression along others, exactly as observed in familiar tidal phenomena. Despite its usefulness, the Newtonian tidal matrix depends on the choice of coordinates and on the notion of force, which itself depends on an assumed background of absolute space and time. When gravity becomes strong, or when motions approach relativistic speeds, this framework becomes inadequate. The relativistic description replaces the gravitational force with space-time geometry. Objects move not because they are pulled by a force, but because they follow the natural straight-line paths, or geodesics, of curved space-time. In this context, the true analogue of the Newtonian tidal matrix is the relativistic tidal tensor constructed from the Riemann curvature tensor. The Riemann curvature tensor is the mathematical object that measures how space-time is curved. It captures how the geometry deviates from flatness in a way that cannot be removed by any choice of coordinates. While its full structure is complex, involving many components, its physical meaning becomes clear when applied to the motion of nearby free-falling particles. The curvature tensor determines how initially parallel geodesics accelerate relative to one another. This relative acceleration is the relativistic definition of tidal force. The equation that formalizes this idea is known as the geodesic deviation equation. It describes how the separation vector between two neighboring geodesics evolves as the particles move through spacetime. Importantly, this equation contains no reference to gravitational force. Instead, it involves the curvature tensor acting on the separation vector and the particle's forward velocity. The result is a relative acceleration that depends solely on spacetime curvature. In other words, tides are not caused by forces acting on particles, but by the geometry of spacetime determining how nearby freefall paths diverge or converge. This shift in perspective has profound implications. In Newtonian physics, one can always imagine transforming to a freely falling frame in which gravity disappears locally. In general relativity, this idea survives in a limited sense. At any single point along a world line, it is always possible to choose a local inertial frame in which the laws of physics reduce to those of special relativity and gravitational forces vanish. However, this cancellation applies only at a point, not over a finite region of space or time. The curvature of space-time ensures that even in a freely falling frame, neighbouring points experience relative accelerations. These relative accelerations are precisely what the geodesic deviation equation describes. This leads directly to the statement that curvature, not force, is the invariant quantity in gravity. Forces can be transformed away locally by choosing an appropriate frame of reference. Curvature cannot. If spacetime is curved, no coordinate transformation can make it flat everywhere. Tidal effects therefore represent the irreducible content of gravity. They are what remains when all coordinate-dependent artifacts have been removed. An intuitive way to understand this is to imagine two freely falling particles released side by side. In flat spacetime, their separation remains constant. In curved spacetime, their separation changes even though neither particle experiences any force in its own frame. This change in separation is a physical effect that all observers agree upon. It cannot be eliminated by redefining coordinates or choosing a different state of motion. The curvature of spacetime dictates the outcome. The stretching and compression of free-falling frames is a direct consequence of this curvature. Consider a small cloud of test particles released simultaneously and allowed to fall freely. As time passes, the cloud may elongate in one direction and contract in others. This deformation occurs even though each particle individually follows a geodesic and feels no force. The pattern of deformation reflects the eigenvalues and eigenvectors of the tidal tensor, which in turn are determined by the local curvature of spacetime. In spherically symmetric spacetimes, such as those around isolated stars or black holes, the tidal pattern has a characteristic form. There is stretching along the radial direction and compression in the transverse directions. This mirrors the Newtonian picture, but arises from purely geometric considerations. The radial stretching corresponds to geodesics that begin at slightly different radii, accelerating away from one another. The transverse compression corresponds to geodesics that begin side by side, converging as space-time curvature focuses them inward. The concept of a local inertial frame is central to understanding both the power and the limitations of this description. Locally, over sufficiently small regions of space-time, curvature effects become negligible. In such regions, space-time appears approximately flat, and special relativity applies. This is why freely falling observers experience weightlessness, and why local experiments cannot detect gravity directly. However, as soon as one considers a region large enough for curvature to matter, tidal effects appear. The inability to extend a single inertial frame over a finite region without encountering relative accelerations is a direct reflection of space-time curvature. This failure of local inertial frames to remain inertial globally is not a technical inconvenience, it is the defining feature of gravity in general relativity. If gravity were merely a force, one could imagine transforming it away everywhere by choosing a suitable frame. The fact that this is impossible reveals that gravity is encoded in the structure of space-time itself. Nowhere is this more evident than in the vicinity of black holes. In the relativistic description, a black hole is not characterized primarily by strong gravitational forces, but by extreme space-time curvature. Outside the event horizon, space-time curvature increases steadily as one approaches the central mass. Inside the horizon, curvature inevitably grows without bound as the singularity is approached. Importantly, black holes exhibit curvature even in vacuum. The region outside a black hole contains no matter in the classical sense, yet space-time is profoundly curved. This vacuum curvature is described by solutions to Einstein's equations in which the stress-energy tensor vanishes, but the curvature tensor does not. The Schwarzschild solution is the simplest example. It represents a spherically symmetric black hole in empty space, with curvature entirely determined by the black hole's mass. This vacuum curvature is responsible for all tidal effects near black holes. An object falling toward a black hole experiences no force in its own frame, but its internal structure is subject to increasing tidal stress as curvature gradients intensify. For sufficiently massive black holes, these tidal stresses may remain small at the event horizon, allowing an object to cross without immediate destruction. For smaller, denser black holes, tidal stresses can become overwhelming well outside the horizon. The distinction between force and curvature becomes crucial here. From the perspective of a distant observer, the gravitational field near a black hole appears immense. From the perspective of a freely falling observer, there is nothing locally dramatic about crossing the horizon itself. What matters physically is not the presence of a horizon, but the magnitude of the curvature. Tidal forces track curvature, not coordinate-defined notions of gravitational strength. The relativistic tidal tensor makes this precise. It quantifies how rapidly geodesics diverge or converge in different directions, independent of coordinates or observer motion. Its components grow as curvature grows, signaling increasing tidal stress. Near the singularity, these components diverge, indicating that no extended object can maintain coherence. The destruction of structure in such environments is therefore not a consequence of being pulled by gravity, but of space-time itself becoming too curved to support stable separation between neighbouring world lines. This geometric view also clarifies why tidal effects are unavoidable. Even if an object is in perfect free fall, even if it experiences no acceleration relative to its own frame, it cannot escape curvature-induced deformation. The internal distances within the object are defined by space-time geometry, and when that geometry varies significantly across the object's size, internal stresses arise. These stresses are not forces in the Newtonian sense, but they are just as physically real. In weak gravitational fields, the Newtonian tidal matrix provides an excellent approximation to the relativistic tidal tensor. The two descriptions agree quantitatively when velocities are low and curvature is small. As conditions become more extreme, the relativistic description remains valid, while the Newtonian picture fails. This continuity ensures that tidal physics can be understood as a single framework, with Newtonian tides emerging as a limiting case of space-time curvature. Ultimately, the tidal tensor and the geodesic deviation equation reveal what gravity fundamentally is. Gravity is not primarily about attraction or force. It is about how space-time tells nearby free-falling objects to move relative to one another. Tidal effects are the clearest operational signature of this fact. They persist in freefall, they cannot be transformed away, and they encode the curvature of space-time in a directly measurable way. As gravitational environments become more extreme, tidal effects cease to be subtle corrections and instead dominate the dynamics. In such regimes, the curvature of space-time itself becomes the agent of destruction and transformation, stretching, compressing, and ultimately erasing structure. From the gentle tides of Earth's oceans to the violent spaghettification near black holes, the same geometric principle applies. Tidal forces are gravity stripped of illusion, revealing curvature as the true engine behind gravitational phenomena. The concept of a Roche limit emerges naturally once tidal forces are treated not as abstract gradients, but as agents capable of overcoming the internal forces that hold an object together. It represents a boundary in space where the differential gravitational pull from a primary body becomes strong enough to overwhelm the self-binding of a secondary body. Unlike event horizons or physical surfaces, the Roche limit is not a sharp line. It is a threshold defined by competing stresses, and its exact location depends on the internal structure, composition, and dynamical state of the object approaching it. The classical derivation of the Roche limit assumes an idealized scenario, a fluid satellite orbiting a much more massive primary body in a circular orbit. The satellite is assumed to have no internal material strength, meaning it behaves like a self-gravitating fluid that can freely deform under stress. In this limit, cohesion is provided entirely by the satellite's own gravity. This assumption is not arbitrary. At sufficiently large scales, material strength becomes negligible compared to gravitational forces, making the fluid approximation accurate for moons, stars, and planets over long timescales. In this framework, the Roche limit is obtained by equating the satellite's self-gravitational acceleration at its surface to the tidal acceleration imposed by the primary across the satellite's diameter. The satellite's self-gravity acts to pull material inward, maintaining coherence. The tidal field of the primary acts to pull material apart along the line connecting the two bodies. When the tidal stretching exceeds the restoring pull of self-gravity, the satellite can no longer maintain a stable shape. Quantitatively, the result depends on the densities of the two bodies. For a fluid satellite of density comparable to that of the primary, the Roche limit lies at a distance of roughly 2.44 times the radius of the primary. This numerical factor arises from the geometry of tidal deformation and the assumption of hydrostatic equilibrium. Importantly, the limit scales with density rather than mass alone. A dense satellite can approach closer than a diffuse one before disruption, even if both have the same mass. This density dependence reveals the physical meaning of the Roche limit. It is not about absolute gravitational strength, but about gradients relative to internal cohesion. A low-density object is loosely bound by its own gravity and is therefore more vulnerable to tidal forces. A high-density object resists deformation more effectively, allowing it to survive deeper in a gravitational well. The classical Roche limit applies strictly to fluid bodies, but real objects span a wide spectrum of internal structures. Rigid bodies, rubble pile aggregates, and fluids respond very differently to tidal stress, and their effective Roche limits differ accordingly. Rigid bodies possess internal material strength that supplements self-gravity. Rocks, metals, and ice can support shear and tensile stress, at least up to a point. For such objects, tidal forces must overcome both gravitational binding and material strength before disruption occurs. This allows rigid objects to survive inside the classical fluid Roche limit, sometimes by a significant margin. Small moons, asteroids, and artificial satellites routinely exist well within distances that would be forbidden to fluid bodies. However, rigidity is scale-dependent. Material strength does not scale with size in the same way gravity does. As objects grow larger, gravitational stresses increase faster than material strength. Beyond a certain size, even the strongest materials behave effectively as fluids under sustained stress. This is why planets are round, and why large moons relax into equilibrium shapes over geological timescales. For these bodies, the fluid Roche limit becomes the relevant criterion. Rubble pile objects occupy an intermediate regime. These bodies are not monolithic solids, but loosely bound collections of fragments held together primarily by weak self-gravity and limited friction between components. Many asteroids fall into this category. Rubble piles have little tensile strength, but they can resist compression to some degree through contact forces. Under tidal stress, they deform easily, rearranging internally long before catastrophic disruption occurs. As a rubble pile object approaches a massive body, tidal forces first induce elongation and internal reconfiguration. Voids open, material migrates, and the object may shed mass gradually rather than breaking apart explosively. The effective Roche limit for rubble piles is therefore less sharply defined than for fluids or rigid bodies. Disruption can begin well outside the classical fluid Roche limit and proceed over multiple orbits. Rotation adds another layer of complexity. A rotating body experiences centrifugal forces that partially counteract gravity. If the rotation is rapid, effective gravity at the equator is reduced, making the body more vulnerable to tidal disruption. This is particularly important for tidally evolving systems, where rotation rates can change over time due to tidal torques. Tidal locking plays a central role here. As a satellite orbits a primary, tidal interactions tend to synchronize its rotation period with its orbital period. Once locked, the same face of the satellite always points toward the primary. This configuration minimizes energy dissipation for a given angular momentum state, and is therefore dynamically favored. In a tidally locked satellite, the tidal stress pattern becomes fixed relative to the body. The satellite develops a permanent tidal bulge aligned with the primary. This static deformation redistributes internal stresses and can either stabilize or destabilize the object, depending on circumstances. If the satellite lies near its Roche limit, tidal locking can enhance elongation and accelerate structural failure by maintaining maximal stress orientation. Before complete disruption occurs, tidal forces often deposit significant energy into the object through tidal heating. As the body deforms under the varying gravitational field, internal friction and viscous dissipation convert mechanical energy into heat. This process can raise internal temperatures dramatically, altering material properties and weakening structural integrity. Tidal heating is most effective when the deformation is time-dependent, such as in eccentric orbits or during orbital decay. Each close passage subjects the object to changing tidal stresses, pumping energy into its interior. Over time, this heating can melt ice, soften rock, or vaporize volatile components. In moons, tidal heating can drive geological activity, as seen in volcanically active bodies orbiting giant planets. In objects nearing disruption, tidal heating acts as a preparatory mechanism, reducing internal cohesion before mechanical failure occurs. As disruption begins, material is stripped from the object and placed onto independent orbits around the primary. Conservation of angular momentum ensures that this debris does not fall directly inward. Instead, it spreads into elongated streams that can intersect, collide, and gradually circularize. Over time, these processes can lead to the formation of rings. Ring formation from disrupted moons is a natural outcome of Roche limit physics. Inside the Roche limit, self-gravity is too weak to allow reaccumulation into a coherent moon. Outside the Roche limit, debris can clump and reform. This creates a spatial segregation. Rings persist inside the Roche limit, while moons exist outside it. The structure of rings reflects this balance. Collisions between particles dissipate energy while conserving angular momentum, flattening the debris into a thin disk. Differential orbital motion spreads material azimuthally, producing rings that can persist for long periods if replenished or stabilized by resonances. Saturn's rings provide the most striking example of a long-term tidal equilibrium. They lie almost entirely within Saturn's Roche limit for icy material. The particles composing the rings are predominantly ice, with densities low enough that self-gravity cannot overcome Saturn's tidal field. As a result, accretion into a moon is suppressed, and the ring system remains fragmented. At the same time, the rings are not static. Collisions, gravitational resonances with Saturn's moons, and interactions with Saturn's magnetic environment continuously reshape their structure. Gaps, waves, and sharp edges emerge from the interplay between tidal forces and orbital dynamics. Despite this activity, the overall ring system remains stable on timescales long compared to human history, illustrating that tidal disruption does not necessarily imply rapid destruction. Under the right conditions, it can produce enduring structures. Saturn's rings may have originated from the disruption of a former moon, or from material left over from planetary formation. Regardless of their origin, their persistence demonstrates that the Roche limit is not merely a destructive boundary, it is also a zone of organization, where matter is forced into specific configurations by gravitational gradients. The Roche limit therefore represents a broader principle. It marks the transition between regimes where self-gravity dominates structure formation and regimes where tidal forces dominate. Inside this limit, matter cannot easily assemble into large coherent bodies. Outside it, accretion becomes possible. This principle applies not only to moons and rings, but to stars near black holes, gas clouds in galaxies, and even dark matter substructures in cosmic halos. Structural failure near the Roche limit is not instantaneous. It unfolds through deformation, heating, fragmentation, and redistribution. Each stage reflects a balance between internal binding and external tidal stress. The exact pathway depends on composition, size, rotation, and orbital history. What unifies these outcomes is the underlying tidal physics. By examining Roche limits and the modes of structural failure they induce, tidal forces cease to be abstract gradients and become agents of transformation. They do not simply tear objects apart. They determine what kinds of structures can exist where, for how long, and in what form. From shattered moons to elegant ring systems, the imprint of tidal limits is written across planetary systems and far beyond them. In the dense environments of galactic nuclei, tidal forces cease to be a background influence and instead become dominant agents of stellar destruction. At the centers of most galaxies resides a supermassive black hole surrounded by a dense cluster of stars moving on a wide range of orbits. These stars are not on orderly, coplanar paths. Their trajectories are continually perturbed by gravitational interactions with one another, by the collective potential of the nuclear star cluster, and by any surrounding gas or stellar remnants. Over long timescales, these perturbations slowly change the angular momenta of stellar orbits, allowing some fraction of stars to wander into configurations that bring them dangerously close to the central black hole. This slow diffusion of orbits through angular momentum space is known as loss cone dynamics. The loss cone is a region of phase space corresponding to orbits whose pericenter distances fall below a critical threshold, typically comparable to the tidal disruption radius of the black hole. If a star enters this region, it is destined for destruction. The term cone reflects the geometry of velocity space. Only stars with sufficiently small angular momentum relative to their orbital energy can plunge deep enough toward the black hole to be tidally disrupted. In a perfectly collisionless system, the loss cone would rapidly empty and remain depleted. In real galactic nuclei, however, gravitational encounters continually scatter stars into and out of lost cone orbits, maintaining a steady though rare supply of stars for tidal disruption events. Once a star's orbit carries it into the lost cone, the decisive moment occurs at pericenter, the point of closest approach to the black hole. As the star falls inward, the tidal field intensifies rapidly due to its inverse cube scaling with distance. Well before the star reaches the event horizon, tidal stresses can exceed the star's self-gravity. At this point, the star begins to deform dramatically. The leading edge, closer to the black hole, experiences a stronger gravitational pull than the trailing edge, resulting in extreme elongation along the radial direction. Simultaneously, the star is compressed laterally, both within the orbital plane and perpendicular to it. This elongation is not a gentle stretching. For deep encounters, the star can be drawn out into a long, thin filament whose length exceeds its original diameter by orders of magnitude. The timescale for this deformation is comparable to the star's own dynamical timescale, meaning that the response is violent and non-linear. Internal pressure gradients cannot adjust smoothly, and the star's structure is driven far from equilibrium. A particularly striking aspect of stellar tidal disruption is vertical compression, often referred to as pancaking. As the star passes through pericenter, the tidal field compresses it in the direction perpendicular to the orbital plane. This occurs because space-time curvature focuses trajectories toward the plane of motion. The result is a rapid collapse of the stellar material along this axis, producing a brief but intense increase in central density and temperature. This vertical compression can be extreme. Numerical simulations show that in sufficiently deep encounters, the core of the star can be compressed to densities far exceeding its normal hydrostatic values. The compression happens on a timescale shorter than the star's ability to radiate energy away, leading to near adiabatic heating. In some cases, temperatures can rise high enough to ignite nuclear reactions that would not occur under ordinary stellar conditions. The rapid compression and subsequent rebound generate strong shocks within the stellar material. These shocks propagate through the elongated debris, dissipating kinetic energy and further heating the gas. In main-sequence stars, this process may produce transient thermonuclear flashes, though the total energy released is generally small compared to the star's gravitational binding energy. In more compact stars, such as white dwarfs, tidal compression can be far more dramatic. Under the right conditions, it may trigger runaway nuclear burning, leading to partial or complete detonation before the star is fully disrupted. As the star is torn apart, its material does not simply disappear into the black hole. The tidal field redistributes energy across the stellar debris in a highly systematic way. Roughly half of the stellar mass gains enough energy to become unbound and escape on hyperbolic trajectories. The other half remains gravitationally bound to the black hole, spread across a range of highly eccentric orbits. This division is a direct consequence of the energy gradient imposed across the star at pericenter. The distribution of specific orbital energies in the bound debris is nearly flat over a characteristic range. This property has important consequences for the subsequent evolution of the system. As bound debris follows its elongated orbits, it returns to pericenter at different times depending on its orbital period. The most tightly bound material returns first, followed by progressively less bound material. The rate at which debris falls back toward the black hole, known as the fallback rate, follows a characteristic power law decay with time. This fallback rate sets the time scale and luminosity evolution of the tidal disruption event. Initially, the fallback can be extremely rapid, delivering mass to the vicinity of the black hole at rates that exceed the Eddington limit, the theoretical maximum steady accretion rate set by radiation pressure. During this phase, the system may drive powerful outflows or winds that carry away excess mass and energy. As time progresses and the fallback rate declines, accretion becomes more orderly and radiatively efficient. As the returning debris streams intersect near pericenter, they collide and shock, dissipating orbital energy while conserving angular momentum. These collisions are essential for circularization, the process by which highly eccentric debris orbits evolve into a more circular accretion disk. The efficiency of circularization depends on relativistic effects, orbital orientation, and the depth of the encounter. In relativistic regimes, apsidal precession causes successive debris streams to intersect at different angles, enhancing shock dissipation and accelerating disk formation. Relativistic precession plays a crucial role here. In Newtonian gravity, elliptical orbits are closed and debris streams would retrace their paths without intersecting efficiently. Near a black hole, space-time curvature causes the pericenter of each orbit to precess. As a result, returning streams collide with incoming ones at significant angles, converting kinetic energy into heat. This process is one of the primary mechanisms by which orbital energy is dissipated and a luminous accretion flow is established. Once an accretion disk forms, it becomes the dominant source of radiation. Gravitational potential energy is converted into thermal energy as matter spirals inward, eventually being radiated away across a broad range of wavelengths. The precise spectral output depends on the black hole mass, the accretion rate, and the structure of the disk. Emission may peak in the ultraviolet or soft X-ray bands for lower mass black holes, while higher mass systems may radiate more strongly in optical wavelengths due to cooler disk temperatures. The observational appearance of a tidal disruption event evolves over time. The initial flare can rise rapidly as fallback begins, reaching peak luminosities comparable to those of supernovae or even active galactic nuclei. Peak luminosities are typically constrained by the Eddington limit, though brief super-Eddington phases are possible due to anisotropic emission or outflows. After peak, the luminosity declines roughly in step with the fallback rate, often following a power law decay over months to years. These timescales are a defining feature of tidal disruption events. Unlike supernovae, which fade over weeks to months, or persistent active nuclei, which can shine for millions of years, tidal disruption events occupy an intermediate regime. Their extended light curves reflect the gradual return and accretion of stellar debris. This temporal behavior provides a powerful diagnostic of the underlying tidal physics and allows astronomers to distinguish tidal disruption events from other transient phenomena. Luminosity limits also encode information about the black hole and the disrupted star. The maximum luminosity is tied to the black hole's mass through the Eddington limit, while the duration and decay rate depend on the stellar mass and radius. More massive stars produce larger debris masses and longer-lasting events. More compact stars experience stronger tidal gradients and may produce faster, more violent flares. Importantly, not all stellar encounters with black holes lead to full disruption. Grazing encounters can strip material from the star without destroying it entirely, leading to partial tidal disruption events. In such cases, the star may survive and return on a modified orbit, potentially undergoing repeated mass loss episodes. These events further broaden the range of observational signatures associated with tidal interactions in galactic nuclei. Stellar tidal disruption events thus represent a convergence of many aspects of tidal physics. Loss cone dynamics sets the rate at which stars are delivered to the black hole. Differential gravity at pericenter drives extreme elongation and compression. Shock formation and heating reshape stellar material on dynamical timescales. Energy redistribution determines which debris escapes and which feeds the black hole. Relativistic effects govern disk formation and emission. Together, these processes transform an ordinary star into a transient beacon that briefly illuminates the otherwise dark environment of a galactic nucleus. In this context, tidal forces are not merely destructive. They act as probes of extreme gravity, revealing the presence and properties of otherwise quiescent black holes. By studying the light curves, spectra, and timescales of tidal disruption events, it becomes possible to infer black hole masses, test relativistic dynamics, and observe stellar material under conditions unattainable in any other setting. The death of a star, driven by tides, becomes a source of information about the deepest gravitational wells in the universe. The term spaghettification is often treated as informal or even playful, but it describes a very specific and rigorously defined physical process. At its core, spaghettification is the extreme manifestation of tidal deformation, in which differential gravitational acceleration produces anisotropic strain within an extended object. This strain is not uniform in all directions. It has a well-defined geometry, characterized by stretching along one axis and compression along others. Understanding this geometry precisely is essential to separating physical reality from metaphor. The deformation experienced by an object in a strong tidal field can be decomposed into axial strain and transverse strain. Axial strain refers to deformation along the direction of the tidal gradient, which in astrophysical contexts is typically the radial direction toward the gravitating mass. Transverse strain refers to deformation in directions perpendicular to this axis. These two components are not independent. They are linked by the structure of the gravitational field and, in relativistic terms, by the curvature of space-time. In a spherically symmetric gravitational field, the tidal tensor has one positive eigenvalue and two negative eigenvalues. The positive eigenvalue corresponds to stretching along the radial axis. The negative eigenvalues correspond to compression in the two transverse directions. This is not a coincidence or a choice of coordinates. It follows from the requirement that the gravitational field satisfy conservation laws and, in Newtonian gravity, from the fact that the divergence of the gravitational field in vacuum vanishes. In general relativity, it follows from the trace-free nature of the tidal tensor in vacuum spacetimes. The consequence is that any freely falling extended object near a compact mass will be pulled apart along the radial direction while being squeezed laterally. The net volume change may be small initially, but the shape distortion becomes extreme as tidal gradients increase. This anisotropic deformation is the defining feature of spaghettification. Elongation dominates perception because the axial strain grows faster and becomes visually overwhelming long before transverse compression reaches comparable perceptual significance. Human intuition is strongly biased toward changes in length rather than changes in cross-sectional area. A body stretched to many times its original length immediately suggests tearing or pulling apart, even if its width has only decreased modestly by comparison. In physical terms, the axial strain increases linearly with separation distance and inversely with the cube of the distance to the gravitating mass. As the object approaches regions of stronger curvature, this scaling drives rapid elongation. Transverse compression, while equally real, acts in two dimensions simultaneously. The cross-sectional area shrinks, but this shrinkage is often less intuitively dramatic than axial stretching. Nonetheless, transverse compression plays a critical role in the internal physics of spaghettification. It raises internal pressures, increases temperature, and accelerates the breakdown of structural cohesion. In extreme cases, transverse compression can become violent enough to trigger shock formation or even nuclear reactions, as seen in some tidal disruption scenarios. A crucial distinction in describing spaghettification is the difference between proper length and coordinate length. Coordinate length is the distance between 2 points as measured in a chosen coordinate system, which may be distorted by the geometry of spacetime. Proper length is the physical distance measured locally by an observer using rulers carried along with the object. Only proper length corresponds to physically meaningful stretching experienced by the object itself. Near strong gravitational fields, coordinate descriptions can be misleading. An external observer using distant coordinates may describe an object as appearing frozen, compressed, or stretched in ways that do not correspond to what the object itself experiences. Spaghettification, however, is defined by changes in proper length. The separation between neighbouring elements of the object, as measured locally, increases along the radial direction and decreases transversely. These changes are invariant and cannot be transformed away by choosing a different coordinate system. This distinction is particularly important near black holes, where coordinate artifacts become extreme. From a distant observer's perspective, an infalling object may appear to slow down and stretch near the event horizon. From the object's own perspective, crossing the horizon involves no special event, but the tidal deformation it experiences depends entirely on the local curvature. If the curvature is weak, proper lengths remain nearly unchanged. If the curvature is strong, proper lengths diverge rapidly. Spaghettification is therefore a statement about curvature-induced deformation, not about coordinate-dependent appearances. As tidal gradients increase, the internal stresses within the object do not merely grow large. They diverge in finite, proper time. This is a critical point. Spaghettification is not an asymptotic process that stretches an object indefinitely without completion. For sufficiently strong tidal fields, the differential acceleration between neighbouring points grows without bound as the object approaches regions of high curvature. The result is that internal stresses exceed any finite binding force in a finite amount of time. This finite time divergence follows directly from the geodesic deviation equation. The relative acceleration between nearby world lines depends on the curvature tensor. When curvature components grow large, the second derivative of the separation vector becomes large as well. Integrating this equation shows that separations can diverge rapidly, even if initial separations are small. No gradual adaptation or redistribution of stress can prevent this outcome once curvature exceeds critical thresholds. The breakdown of cohesion proceeds through identifiable stages. At first, elastic deformation dominates. Molecular bonds stretch and compress within their elastic limits. As strain increases, plastic deformation sets in. Bonds break and reform, internal structures rearrange, and irreversible damage accumulates. At still higher strain rates and magnitudes, cohesive forces fail catastrophically. Biological cohesion is the first to fail. Tissues rely on relatively weak chemical bonds and organized cellular structures. These fail under stresses far smaller than those required to disrupt bulk materials. Long before spaghettification becomes extreme, any biological organism would lose structural integrity. Cells rupture, membranes tear, and macroscopic anatomy ceases to exist as a coherent system. Molecular cohesion follows. Chemical bonds have characteristic strengths set by electromagnetic interactions. These bonds can withstand significant forces, but tidal stresses scale with size. As an object is stretched, the separation between bonded atoms increases differentially across the object. When the work done by tidal forces over molecular distances exceeds bond energies, molecules dissociate, solids fracture, liquids vaporize, and gases ionize. At still higher tidal gradients, even nuclear cohesion can be challenged. Nuclear forces are enormously strong compared to chemical bonds, but they act over extremely short ranges. In sufficiently extreme tidal fields, such as those near compact astrophysical objects, differential acceleration across nuclear dimensions can become non-negligible. In these regimes, nuclei themselves may be distorted or disrupted, and matter transitions into exotic states governed by fundamental interactions rather than chemistry. The progression from biological failure to molecular dissociation to nuclear disruption is not speculative. It follows directly from the scaling of tidal forces with object size and proximity to the gravitating mass. Larger structures fail first because they span larger gradients. Smaller structures persist longer, but none are immune once curvature becomes sufficiently strong. This is why the language of stretching and tearing is physically accurate rather than metaphorical. Spaghettification does not involve a vague pulling apart. It involves differential acceleration that literally increases the distance between neighbouring elements along one axis while decreasing it along others. The internal stresses generated by this deformation exceed binding forces, causing real mechanical failure. Material lines are stretched, cross-sections are compressed, and the object's topology changes irreversibly. The term tearing captures the fact that cohesion is lost along specific directions. Bonds are not broken uniformly. They are broken preferentially along planes and axes determined by the tidal tensor. This anisotropy is a defining feature of tidal destruction. Objects are not crushed into formless blobs. They are drawn out into elongated streams, sheets, or filaments, reflecting the underlying geometry of the tidal field. Spaghettification therefore has a precise physical meaning. It is the regime in which axial tidal strain dominates internal dynamics, leading to extreme elongation, while transverse compression amplifies internal stress and accelerates failure. It is defined by changes in proper length driven by space-time curvature, not by coordinate effects or observer-dependent descriptions. It proceeds through finite-time divergence of internal stresses, culminating in the loss of all forms of cohesion from biological organization to nuclear structure. Seen in this light, spaghettification is not an exotic curiosity reserved for black holes alone. It is the logical endpoint of tidal physics under sufficiently extreme conditions. The same mathematical framework that describes gentle ocean tides predicts this outcome when gradients become large enough. The difference is not one of principle, but of scale. Spaghettification is tidal deformation pushed beyond every threshold that allows matter to remain whole. The severity of tidal forces near a black hole is not determined simply by how strong gravity feels in a qualitative sense. It is controlled by a precise interplay between space-time curvature, distance from the black hole, and the mass of the black hole itself. Counterintuitively, increasing the mass of a black hole can make its immediate environment less dangerous in tidal terms, at least near the event horizon. This fact lies at the heart of why survival time near a black hole depends so strongly on mass, and why spaghettification is not an inevitable or immediate fate at horizon crossing for all black holes. The starting point is the Schwarzschild radius, the characteristic length scale associated with a non-rotating black hole. This radius defines the location of the event horizon and scales linearly with the black hole's mass. Doubling the mass doubles the Schwarzschild radius. A black hole with a mass comparable to the Sun has a Schwarzschild radius of only a few kilometers, while a supermassive black hole with millions of solar masses has a Schwarzschild radius measured in millions of kilometers. This linear scaling is purely geometric and follows directly from the structure of the Schwarzschild solution to Einstein's equations. Tidal forces, however, do not scale in the same way. The tidal gradient, which governs the relative acceleration between nearby points in freefall, depends on how rapidly space-time curvature changes across space. Near a black hole, this gradient scales inversely with the cube of the distance from the center. When evaluated at the event horizon, that distance is the Schwarzschild radius itself. Substituting the mass-dependent expression for the Schwarzschild radius into the tidal gradient reveals a striking result. The tidal gradient at the horizon scales inversely with the square of the black hole's mass. This inverse relationship means that as black hole mass increases, tidal forces at the horizon become weaker, not stronger. A stellar mass black hole produces enormous tidal gradients at its horizon because its Schwarzschild radius is small. A supermassive black hole spreads the same gravitational influence over a vastly larger region of space, reducing the curvature gradients experienced at any given location near the horizon. The geometry is gentler, even though the total mass is vastly greater. This scaling leads directly to a quantitative contrast between stellar mass and supermassive black holes. Near a stellar mass black hole, the tidal forces at or even outside the event horizon can exceed the structural limits of ordinary matter. An extended object approaching such a black hole experiences extreme differential acceleration well before crossing the horizon. Spaghettification begins far outside the horizon and structural failure occurs on timescales comparable to milliseconds. Near a supermassive black hole, the situation is profoundly different. At the horizon of a black hole with millions or billions of solar masses, the tidal gradient can be small enough that an extended object of human scale experiences negligible internal stress at the moment of crossing. The object remains intact, at least temporarily, as it passes through the horizon. There is no sudden tearing, no dramatic stretching, and no locally detectable marker signalling the transition. From the object's own perspective, horizon crossing is uneventful. This distinction is often misunderstood because it runs counter to intuitive ideas about gravity. The gravitational field near a black hole is often imagined as overwhelmingly strong simply because the black hole is massive. In reality, what matters for tidal survival is not the absolute strength of the gravitational field, but how quickly that field changes over the size of the object. Large black holes change the field slowly across space near their horizons. Small black holes change it rapidly. This also clarifies why density is not the controlling factor. Black holes are sometimes described as extraordinarily dense objects, but this language is misleading. The concept of density inside the event horizon is not well defined in classical general relativity, and even if one assigns an effective density by dividing mass by horizon volume, that density decreases with increasing mass. Supermassive black holes have lower average densities than stellar mass black holes. What determines tidal stress is not how much mass is packed into a given volume in a naive sense, but how space-time curvature varies across space. Mass controls curvature gradients through its influence on the Schwarzschild radius. Increasing mass increases the size of the horizon faster than it increases curvature at that location. As a result, large black holes are less tidally destructive at their horizons. This is why survivability near a black hole depends primarily on mass, not on any intuitive notion of density or compactness. Survival time, however, is not infinite even in the most favourable case. While tidal forces at the horizon of a supermassive black hole may be small, they grow inexorably as the object continues inward. Inside the horizon, all future-directed paths lead toward decreasing radial coordinate values. Space-time curvature increases, and with it, the tidal gradients. Eventually, these gradients become fatal. The relevant measure of time here is proper time, the time measured by a clock carried along with the infalling object. Proper time is invariant and physically meaningful. From the object's own perspective, the journey from the horizon to the region where tidal forces become overwhelming occurs in a finite amount of proper time. The exact duration depends on the black hole's mass and on the object's trajectory. For a stellar mass black hole, the proper time between horizon crossing and catastrophic tidal failure is extremely short, often less than a millisecond. In such cases, the distinction between horizon crossing and destruction is almost academic because destruction occurs so quickly that there is no extended experience of the interior region. The object is effectively torn apart as it approaches the horizon or immediately after crossing it. For a supermassive black hole, the proper time available can be much longer. In principle, it can be measured in seconds, minutes, or even hours, depending on the black hole's mass. During this interval, the object remains in freefall, experiencing gradually increasing tidal stress. There is no way to halt or reverse this progression. Once inside the horizon, escape is impossible, and the increase in curvature is inevitable. The growth of tidal forces inside the horizon follows the same fundamental scaling laws as outside. As the radial coordinate decreases, curvature increases rapidly. The geodesic deviation equation predicts accelerating divergence of neighbouring world lines. Internal stresses rise accordingly. Eventually, the tidal gradient across the object exceeds the strongest binding forces available. and spaghettification begins in earnest. It is important to emphasize that this process is not triggered by the horizon itself. The horizon is a global feature of space-time that marks the boundary of causal influence, not a region of locally extreme physics. Tidal destruction is triggered by curvature reaching critical values. For small black holes, those values are reached early. For large black holes, they are reached deeper inside. This separation between horizon crossing and structural failure resolves many popular misconceptions. There is no universal point at which spaghettification must occur. There is no single distance from the black hole at which all objects are destroyed. The outcome depends on the mass of the black hole, the size of the object, and the strength of its internal cohesion. The same physical laws apply in all cases, but the scales involved differ enormously. The dependence of survivability on mass also explains why black holes of different sizes interact with their environments in qualitatively different ways. Stellar mass black holes embedded in dense environments are efficient at shredding nearby matter, producing bright, compact accretion flows. Supermassive black holes can capture stars whole, at least initially, allowing tidal disruption events to unfold over extended timescales with distinctive observational signatures. Ultimately, survival time near a black hole is governed by geometry. The linear scaling of the Schwarzschild radius with mass, combined with the inverse scaling of tidal gradients with mass at the horizon, sets the stage. Large black holes offer a gentler entry, small black holes offer none. Inside, the geometry tightens inexorably, and the proper time remaining before fatal tidal forces asserts itself is finite and unavoidable. This framework strips spaghettification of its mystique and places it firmly within the logic of relativistic tidal physics. It is not the black hole's density that determines fate, nor the dramatic imagery of an event horizon. It is the mass-dependent structure of space-time curvature and the finite proper time available before that curvature overwhelms all forms of cohesion. The distinction between an event horizon and tidal destruction lies at the heart of many misunderstandings about black holes. These two ideas are often conflated in popular descriptions as if crossing the event horizon were itself a physically violent act, or as if spaghettification were somehow caused by the horizon. In reality, they are fundamentally different concepts. One is a global property of space-time geometry. The other is a local physical process governed by tidal forces. Understanding why they are separate requires careful attention to the role of observers, coordinates, and invariant quantities in general relativity. A useful starting point is the contrast between local and distant observer descriptions. In everyday physics, observers typically agree on what happens and when it happens, aside from small relativistic corrections. Near a black hole, this intuition fails because space-time geometry introduces extreme distortions in how events are labelled by distant coordinates. A distant observer, remaining far from the black hole, describes events using coordinates that extend smoothly to infinity. In these coordinates, an infalling object appears to slow down as it approaches the event horizon. Signals from the object take progressively longer to reach the distant observer, becoming increasingly redshifted and faint. From this viewpoint, the object never quite seems to cross the horizon at all. The infalling object, however, experiences a completely different description. It carries its own clocks and rulers and measures events using local, freely falling coordinates. In this frame, there is no slowing down, no freezing in time, and no divergence of physical quantities at the horizon. The object crosses the horizon after a finite amount of proper time, with nothing locally unusual occurring at that moment. These two descriptions are not contradictory. They are different coordinate representations of the same space-time, and they assign different coordinate labels to the same physical events. This discrepancy highlights the distinction between coordinate singularities and physical singularities. A coordinate singularity arises when a particular choice of coordinates breaks down, even though space-time itself remains smooth. The classic example is the event horizon in Schwarzschild coordinates. At the horizon, certain coordinate components of the metric appear to diverge, giving the impression of a singularity. This divergence is not physical. It disappears when one switches to a different coordinate system that is well behaved at the horizon, such as freely falling coordinates. A physical singularity, by contrast, is characterized by invariant quantities diverging. These quantities do not depend on coordinates or observers. Space-time curvature scalars, tidal forces, and relative accelerations between nearby free-falling particles are examples of invariant measures. When these diverge, no change of coordinates can remove the singular behavior. The central singularity of a black hole, where curvature becomes unbounded, is a physical singularity. The event horizon is not. This distinction immediately clarifies why clocks and rulers behave normally at the horizon. A clock carried by an infalling observer measures proper time, which depends only on the local space-time interval along its world line. At the horizon of a sufficiently massive black hole, space-time curvature is small on human scales. The clock ticks at its usual rate, chemical reactions proceed normally, and local physics follows the laws of special relativity to excellent approximation. A ruler carried along measures proper length between nearby points, and those measurements remain well defined. There is no sudden stretching or compression associated specifically with crossing the horizon. The equivalence principle underpins this behavior. Locally, gravity can always be transformed away by choosing a freely falling frame. This principle does not mean gravity is absent, but it does mean that, over sufficiently small regions of space-time, the effects of curvature are negligible. The event horizon is not a place where curvature must be large. For supermassive black holes, curvature at the horizon can be extraordinarily small. The horizon marks a causal boundary, not a region of extreme local physics. Because of this, there is an absence of detectable horizon markers for infalling observers. No experiment performed entirely within a small laboratory can reveal whether the laboratory is outside or inside the event horizon, at least at the moment of crossing. There is no sudden change in temperature, no spike in radiation, no mechanical stress that signals the transition. The laws of physics continue uninterrupted. This absence of local markers is not an omission or a limitation of our understanding. It is a direct consequence of how event horizons are defined. An event horizon is a global feature of space-time. It is defined by the structure of light cones and causal paths extending into the infinite future. Determining whether a given point lies inside an event horizon requires knowledge of the entire future evolution of space-time. No local measurement can access that information. This is why the horizon is invisible to local physics, even though its consequences are profound on global scales. Popular depictions often blur these distinctions. Black holes are frequently portrayed as cosmic shredders that tear objects apart precisely at the horizon, accompanied by dramatic visual and physical effects. These images are compelling, but they conflate tidal death with horizon crossing. In reality, spaghettification is governed by tidal gradients, which depend on space-time curvature, not on the presence of a horizon. The horizon itself is not a source of tidal force. It is merely the location where escape to infinity becomes impossible. This misconception is reinforced by the way time dilation is often described. From a distant observer's perspective, the infalling object appears to slow down and stretch near the horizon. This apparent stretching is sometimes misinterpreted as physical deformation. In fact, it is a coordinate effect. The distant observer's coordinates assign increasingly large spatial separations to events that are close together in the infalling object's proper frame. The apparent stretching is not something the object itself experiences. Spaghettification, by contrast, is a local, observer-independent process. It is defined by relative acceleration between neighbouring parts of an object, as given by the geodesic deviation equation. If those relative accelerations become large, internal stresses grow and structural failure occurs. all observers, regardless of their state of motion, agree on whether those stresses are present. They may disagree on when or where certain coordinate-defined events occur, but they agree on the physical outcome. This is why spaghettification is independent of observation. It does not depend on how an event is described by a distant observer or an infalling one. It depends on invariant quantities such as curvature and proper acceleration differences. If tidal forces are weak at the horizon, the object survives crossing it. If tidal forces are strong, the object is destroyed before or after crossing, regardless of who is watching. The independence from observation also resolves apparent paradoxes about what distant observers see. A distant observer never sees the infalling object cross the horizon in finite coordinate time. Yet the object does cross in finite proper time. Does spaghettification happen before crossing, after crossing, or never from the distant observer's perspective? The answer is that spaghettification happens in the object's proper frame when tidal forces become large, and this event corresponds to a definite point in space-time. The distant observer may receive light signals from that event increasingly delayed and redshifted, but the event itself is not ambiguous. Its physical reality does not depend on whether it is ever seen. Another common misconception is that the horizon somehow amplifies tidal forces. This idea arises from associating the horizon with strong gravity. In fact, tidal forces track curvature gradients, not gravitational potential or escape velocity. Escape velocity reaches the speed of light at the horizon by definition, but this has no direct bearing on tidal stress. A large black hole can have an enormous escape velocity at its horizon while maintaining extremely small curvature gradients there. Conversely, a small black hole can have lethal tidal forces well outside its horizon. Understanding this separation between horizons and tides also clarifies why black holes of different masses behave so differently. For stellar mass black holes, tidal forces become extreme far outside the horizon. In such cases, spaghettification occurs before any meaningful discussion of horizon crossing. For supermassive black holes, tidal forces at the horizon may be negligible, allowing intact crossing and a prolonged interior journey before tidal death. The horizon plays no causal role in this difference. Mass-dependent curvature does. The absence of horizon markers has further implications. It means that any narrative in which an observer feels the moment of crossing is incorrect. There is no sensation associated with the horizon itself. Any sensations experienced near a black hole are due to tidal stresses, radiation from accretion flows, or interactions with surrounding matter, not to the horizon. In an idealized, isolated black hole, the horizon is locally quiet. This quietness has sometimes been framed as counterintuitive or even disturbing, but it is simply the logical outcome of general relativity. The event horizon is a statement about the causal structure of space-time, not about local dynamics. Confusing the two leads to unnecessary mystery. When tidal death does occur, it does so decisively. The growth of tidal stresses is not gradual in the sense of approaching a limit without reaching it. Once curvature becomes sufficiently large, internal stresses diverge in finite proper time. Structural cohesion fails, first at macroscopic scales and eventually at microscopic ones. This process has a definite onset and outcome, independent of any observer's description. Importantly, this onset does not coincide with any special coordinate-defined surface. It may occur outside the horizon, at the horizon, or well inside it, depending on the system. The location is determined entirely by where tidal gradients exceed binding forces. There is no universal radius at which spaghettification must occur. The clean separation between horizons and tides is one of the conceptual achievements of modern gravitational theory. It shows that gravity is not about dramatic surfaces or hidden traps, but about geometry and invariance. The event horizon is dramatic in its implications for information and causality. but it is physically mundane at the local level. Tidal forces are physically dramatic, but indifferent to global causal boundaries. Seen this way, the black hole environment becomes less mysterious and more coherent. The horizon marks the point of no return, but not the point of destruction. Destruction is governed by curvature, which grows independently of the horizon's location. An object's fate is sealed not by crossing an invisible line, but by the inexorable increase of tidal gradients as space-time geometry tightens. This perspective also reframes how black holes are taught and imagined. Rather than picturing the horizon as a violent boundary, it is more accurate to view it as a silent gate. Nothing special happens there locally, yet everything changes globally. Tidal death, when it comes, is not a consequence of crossing that gate, but of venturing into regions where space-time curvature becomes incompatible with the existence of extended structure. By disentangling event horizons from tidal destruction, it becomes possible to speak precisely about spaghettification without invoking observer-dependent illusions. Spaghettification is a real, local, physical process driven by curvature. Event horizons are real, global, geometric features with no local signature. Confusing the two obscures both. Keeping them separate reveals the internal consistency of relativistic gravity and strips away many of the myths that surround black holes. Once an object has crossed the event horizon of a black hole, the question of escape is no longer meaningful. All future-directed paths lead inward, toward decreasing radial coordinate and increasing space-time curvature. What remains meaningful and physically unavoidable is the evolution of tidal forces along the infalling trajectory. Inside the horizon, tidal divergence is not a possibility or a matter of circumstance. It is inevitable. The internal separation between neighbouring parts of any extended object is driven by space-time geometry toward catastrophic growth in finite proper time. A defining feature of black hole interiors is that the singularity is not infinitely far away in time. From the perspective of an infalling observer, the proper time between horizon crossing and encounter with the singularity is finite. This is a direct consequence of the causal structure of the space-time. Inside the horizon, the radial coordinate behaves like a time coordinate. Decreasing radius is as unavoidable as the passage of time itself. No amount of propulsion, structural reinforcement, or internal force can halt this progression. The exact amount of proper time available depends on the mass of the black hole and the trajectory of infall. For a non-rotating black hole, this time scales roughly with the mass of the black hole. In a stellar mass black hole, the interval may be milliseconds. In a supermassive black hole, it can be seconds or longer. But regardless of scale, the crucial point remains. The remaining proper time is finite, and the endpoint is unavoidable. As the infalling object moves inward, the space-time curvature it encounters increases monotonically. This increase is encoded in the tidal tensor, whose eigenvalues describe how neighbouring geodesics accelerate relative to one another in different directions. Outside the horizon, some eigenvalues may be small, especially near large black holes. Inside the horizon, all relevant curvature components grow without bound as the singularity is approached. The growth of tidal eigenvalues governs the physical experience of deformation. One eigenvalue corresponds to stretching along a particular axis, while others correspond to compression along orthogonal axes. The specific pattern depends on the geometry of the black hole and the infall trajectory, but the qualitative behaviour is robust. In spherically symmetric black holes, the dominant pattern involves extreme stretching along the radial direction and compression in transverse directions. This anisotropy is not a coordinate artifact. It reflects the intrinsic structure of the space-time curvature. As curvature grows, the relative acceleration between neighbouring parts of the object increases. This relative acceleration is what produces internal stress. Unlike external forces, which can sometimes be balanced or redistributed, tidal accelerations act differentially across the object's extent. They pull different parts in different directions with increasing intensity. The geodesic deviation equation predicts that the separation between neighboring world lines will either shrink or grow at an accelerating rate depending on direction. This leads to a critical feature of interior dynamics. Tidal divergence occurs in finite proper time. The separation between neighboring elements does not merely increase without bound asymptotically. It accelerates toward divergence rapidly enough that internal stresses exceed any finite binding force within a finite interval of time. This is not a gradual process that stretches indefinitely. It is a runaway process driven by diverging curvature. Compression accompanies stretching throughout this evolution. While axial stretching tends to dominate intuitive descriptions, transverse compression plays an equally important role. Compression raises internal pressure and temperature, drives shock formation, and alters material properties. In many models, transverse compression becomes violent enough to collapse structures into thinner and thinner cross-sections, amplifying stress concentrations and accelerating failure. As tidal stresses grow, material models that are valid under ordinary conditions begin to fail. At first, classical elasticity may describe deformation. Materials stretch and compress according to familiar stress-strain relations. As stresses exceed elastic limits, plastic deformation takes over. Bonds break and reform. Internal structures rearrange, and energy is dissipated as heat. Soon after, even plastic models lose validity. The strain rates become so high and the stress is so extreme that equilibrium descriptions break down. Matter is no longer able to respond collectively. Instead, it fragments into smaller components whose behavior must be treated statistically or kinetically rather than mechanically. Fluids become turbulent, solids shatter into particulate streams, and gases ionize. At still higher curvature, even these descriptions fail. Molecular cohesion cannot survive once differential acceleration across molecular scales exceeds electromagnetic binding forces. At that point, matter is reduced to plasma. As curvature continues to increase, differential acceleration across nuclear scales becomes relevant. Nuclear binding forces, while enormously strong, act over extremely short distances. In sufficiently extreme tidal fields, even nuclei can no longer be treated as stable, bound entities. This progressive breakdown underscores why no structure can remain coherent inside the horizon. Coherence requires that internal forces be able to maintain fixed relationships between neighboring elements. Tidal divergence explicitly destroys that possibility by imposing relative accelerations that grow faster than any internal force can compensate. The failure is hierarchical. Large-scale structures fail first, followed by smaller and smaller scales. There is no final refuge at which structure becomes immune. Importantly, this outcome does not depend on the composition of the object. Whether the object is biological tissue, solid rock, metallic alloy, degenerate matter, or exotic plasma, the underlying issue is the same. All forms of cohesion rely on forces that operate over finite ranges and have finite strengths. Space-time curvature near a black hole singularity imposes relative accelerations that grow without bound. Any finite strength force is eventually overwhelmed. This inevitability distinguishes tidal divergence inside the horizon from other forms of extreme stress. In many astrophysical environments, destruction occurs because external forces exceed internal binding under particular conditions, but escape or stabilization may still be possible. Inside a black hole horizon, there is no such possibility. The growth of curvature is not contingent on environment or dynamics. It is built into the structure of the space-time. Classical general relativity makes clear predictions about this regime. As the singularity is approached, curvature invariants diverge. Tidal eigenvalues grow without limit. Proper time to the singularity remains finite. These predictions are robust within the classical theory and do not depend on detailed modelling of matter. They arise purely from the geometry of the space-time. At the same time, this is precisely the regime where classical theory is expected to fail. When curvature reaches scales comparable to those associated with quantum gravity, the assumptions underlying general relativity break down. Quantum effects, vacuum polarization, and fluctuations of spacetime itself may become important. The classical singularity may be replaced by some other structure, such as a bounce, a transition to a different phase of spacetime, or a more subtle quantum state. What remains unknown is how tidal divergence behaves in such a quantum gravitational regime. Classical predictions indicate divergence to infinite curvature and infinite tidal stress. Quantum gravity may regulate or modify this behavior. It may smear out singularities, limit curvature growth, or alter the causal structure near the endpoint. At present, there is no complete, experimentally verified theory that describes this regime. However, even these uncertainties do not restore survivability in any meaningful sense. Quantum gravity effects, whatever their form, are expected to become relevant only at extremely small scales and extremely high curvatures. By the time such effects matter, all classical structures would already have been destroyed. The breakdown of biological, molecular, and nuclear cohesion occurs at curvature scales far below those associated with hypothetical quantum gravitational resolution mechanisms. In this sense, quantum gravity does not rescue structure. It may change the ultimate fate of spacetime itself, but it does not prevent tidal destruction of extended objects. The journey from horizon to singularity remains one of inevitable disintegration, regardless of the precise nature of the endpoint. The interior of a black hole therefore represents a regime where the geometric nature of gravity is laid bare. There are no forces in the conventional sense acting on the infalling object. Each element follows a geodesic, yet the object as a whole is torn apart because neighbouring geodesics do not remain parallel. The geometry of space-time itself enforces divergence. This is the final expression of tidal physics. Outside the horizon, tides may or may not be lethal, depending on mass, distance, and scale. Inside the horizon, the increase of curvature is guaranteed, and with it, the growth of tidal stress. No shielding, no structural reinforcement, and no choice of trajectory can alter this outcome. The inevitability of tidal divergence inside the horizon is not dramatic in the sense of sudden violence. It is inexorable rather than explosive. The remaining proper time ticks down steadily as curvature rises, internal stresses grow, and coherence is lost at progressively smaller scales. There is no final moment of survival followed by instant destruction. There is a continuous progression toward a regime where the very concept of an extended object ceases to apply. In classical relativity, this progression ends at the singularity, a boundary of the theory itself. Beyond that boundary, current physics offers no definitive answers. What is certain is that long before that boundary is reached, tidal divergence has erased all familiar forms of structure. Inside the horizon, spaghettification is not a possibility tied to observation or circumstance. It is a geometric certainty built into the fabric of space-time. Tidal forces do not only stretch and tear, they also compress, heat, and fundamentally alter the internal thermodynamic state of matter. In extreme gravitational environments, compression becomes just as important as elongation, and in many cases it is compression rather than stretching that drives the most energetic and observable consequences of tidal encounters. When deformation occurs rapidly enough, ordinary mechanisms of thermal regulation fail, and mechanical work is converted directly into heat. Under the right conditions, this heating can become intense enough to trigger nuclear reactions, reshaping matter at its most fundamental level. Tidal compression acts as a heating mechanism because work is done on matter by differential gravitational forces. When an object is compressed, external forces do work against internal pressure. If that compression occurs faster than the object can radiate energy away or redistribute it internally, the work done increases internal energy. In gravitational systems, this process is often close to a diabatic. Entropy increases, temperature rises, and pressure builds rapidly. Tidal compression therefore behaves like a gravitational piston, converting orbital and gravitational energy into internal thermal energy. The efficiency of this process depends strongly on time scale. Slow compression allows matter to adjust quasi-statically. Heat can be transported away by radiation, convection, or conduction, and temperatures remain relatively moderate. Rapid compression, by contrast, traps energy. Pressure rises faster than heat can escape, forcing the temperature upward. Tidal encounters near compact objects typically operate in this rapid regime. The timescale for deformation can be comparable to or shorter than the object's internal sound crossing time, leaving no opportunity for equilibrium adjustment. During close tidal encounters, compression often occurs in specific directions. As discussed earlier, the tidal tensor imposes stretching along one axis and compression along others. In stellar tidal disruption events, vertical compression perpendicular to the orbital plane can be particularly severe. As the star passes through pericenter, its material collapses inward along this axis, increasing central density and temperature dramatically over a very short interval. The temperature rise during such rapid deformation can be extreme. In a main sequence star, central temperatures under normal conditions are already high enough to sustain nuclear fusion, but only in a stable, regulated manner. Tidal compression can transiently raise temperatures well above their equilibrium values. This additional heating does not immediately balance through expansion because the deformation is externally imposed and dynamically driven. Instead, temperature spikes develop, especially near the core or along compressed axes. This heating is not uniformly distributed. Shock waves form as compressed regions rebound and interact with surrounding material. Shocks are highly effective at converting bulk kinetic energy into thermal energy. When compression drives matter inward faster than pressure can respond smoothly, discontinuities develop and shocks propagate through the material. These shocks further increase temperature and entropy, amplifying the heating initiated by compression alone. In many tidal disruption events involving ordinary stars, the heating is intense but not sufficient to unbind the star through nuclear energy release alone. The dominant energy source remains gravitational, not nuclear. Nonetheless, nuclear reactions can be temporarily enhanced. Fusion rates are extremely sensitive to temperature, often scaling steeply with it. Even a modest increase in temperature can dramatically increase reaction rates, leading to brief thermonuclear flashes. These flashes do not resemble supernova explosions in scale or duration. They are localized, transient, and energetically subdominant. However, they can alter the chemical composition of the disrupted material, producing isotopic signatures that may later be observable in spectra. In this way, tidal compression leaves a nuclear imprint even when it does not dominate the energy budget. The situation becomes far more dramatic when the disrupted object is a white dwarf. White dwarfs are supported not by thermal pressure, but by electron degeneracy pressure. They are extremely compact, with densities far exceeding those of ordinary stars. This compactness makes them resistant to tidal disruption by supermassive black holes, but vulnerable to tidal interactions with intermediate mass black holes. In such encounters, tidal compression can reach levels sufficient to ignite runaway nuclear burning. When a white dwarf experiences strong tidal compression, particularly along one or more axes, its density and temperature can rise sharply. Unlike main sequence stars, white dwarfs lack the ability to regulate this heating through expansion. Degenerate matter does not expand appreciably in response to heating until degeneracy pressure is overcome. As a result, temperature increases do not immediately reduce pressure, creating conditions for thermonuclear runaway. Under the right conditions, tidal compression can ignite carbon or oxygen fusion in the white dwarf's interior. Once ignition occurs, energy release accelerates rapidly, driving further heating and reaction rates. This positive feedback can lead to a tidal detonation in which nuclear burning propagates explosively through the star. The outcome can resemble a supernova-like explosion, though with distinct energetics and geometry. Tidal detonation scenarios are of particular interest because they offer a mechanism for producing thermonuclear explosions without the traditional triggers associated with stellar evolution. The explosion is driven not by mass accretion or internal instability, but by external gravitational compression. The geometry of the explosion can be highly asymmetric, reflecting the directional nature of tidal forces. Shock-driven nucleosynthesis plays a key role in these extreme environments. As shocks propagate through compressed stellar material, they create conditions far from equilibrium. Temperatures and densities briefly reach levels where nuclear reactions proceed along unusual pathways. Elements can be synthesized that would not normally form in stable stellar interiors. These processes can alter elemental abundances and isotopic ratios in the debris. The products of such nucleosynthesis are carried away with the tidal debris. Some of this material escapes the black hole entirely, dispersing into the surrounding galactic environment. Over time, it may contribute to chemical enrichment on larger scales. While the total mass involved in a single tidal disruption event is small compared to galactic scales, repeated events over cosmic time can leave a cumulative imprint. Despite the dramatic nature of these processes, there are clear limits to the energy they can release. Nuclear energy, while substantial, is finite and bounded by the mass and composition of the disrupted object. Gravitational binding energy near a black hole often exceeds the total nuclear energy available. As a result, even the most violent tidal detonations do not rival the most energetic astrophysical explosions in absolute terms. Moreover, not all tidal encounters lead to nuclear ignition. The outcome depends sensitively on the mass of the black hole, the type of star involved, the depth of the encounter, and the trajectory. For main sequence stars around supermassive black holes, nuclear effects are typically secondary. For white dwarfs around intermediate mass black holes, they can be dominant. The parameter space is broad, and only certain regions produce explosive outcomes. Observationally, compression-driven heating and nuclear effects manifest in distinctive ways. Thermal emission from heated debris produces luminous flares across optical, ultraviolet, and X-ray wavelengths. Shock heating can generate hard radiation components and broaden spectral lines. Nuclear burning can introduce transient spectral features associated with specific elements or isotopes. In tidal detonation scenarios, the light curve may resemble that of a supernova, but with notable differences. The rise and decay timescales can be shorter or longer, depending on the geometry and mass involved. The spectral evolution may lack features associated with expanding stellar envelopes, instead reflecting rapidly evolving asymmetric debris flows. These signatures provide a means of distinguishing tidal detonations from more conventional explosive events. Even in non-detonating tidal disruptions, heating leaves observable imprints. The fallback and accretion of heated debris onto the black hole produces sustained emission. The temperature of the accretion flow influences the emitted spectrum, shaping the relative contributions of different wavelength bands. Observations of these spectra allow inferences about the degree of heating and the efficiency of energy conversion. There are also indirect observational consequences. Heating affects the dynamics of debris streams by altering pressure and sound speed. This, in turn, influences how efficiently debris circularizes and forms an accretion disk. Strong heating can thicken debris streams, enhance shocks, and accelerate disk formation. Weak heating can delay these processes, leading to prolonged, irregular emission. From a broader perspective, compression and heating demonstrate that tidal forces are not purely destructive in a mechanical sense. They are transformative. By injecting energy into matter, they create new thermodynamic and nuclear states that would otherwise be inaccessible. They convert orbital energy into heat, heat into radiation, and in extreme cases, heat into nuclear transmutation. At the same time, these processes are tightly constrained. They operate within clear physical limits set by timescale, composition, and energy budgets. Tidal heating does not lead to unlimited energy release. It channels existing gravitational energy into other forms, reshaping matter but not violating conservation laws. In the context of spaghettification and tidal destruction, compression and heating provide a crucial counterbalance to the emphasis on stretching. Matter near compact objects is not simply pulled apart into cold filaments. It is squeezed, shocked, heated, and chemically transformed. These effects determine what survives, what radiates, and what ultimately escapes to be observed. Taken together, tidal compression, rapid heating, and nuclear effects complete the picture of tidal encounters as multifaceted physical processes. They link gravity to thermodynamics and nuclear physics, showing how space-time curvature can drive matter across regimes of behavior that span from classical mechanics to the thresholds of nuclear reactions. In doing so, they turn tidal destruction into one of the universe's most efficient engines for converting gravitational structure into observable phenomena. Neutron stars and white dwarfs occupy a regime where tidal forces probe matter under conditions unattainable elsewhere. These objects are not simply dense versions of ordinary stars. Their internal structure is governed by extreme equations of state, where pressure arises from quantum mechanical effects, relativistic degeneracy, and strong nuclear interactions. When tidal forces act on such matter, the response is qualitatively different from that of normal stellar material. Deformation, heating, and failure occur not only at macroscopic scales, but also at the level of microscopic degrees of freedom that define the star's internal state. The equation of state determines how matter responds to compression and shear. In white dwarfs, pressure support is dominated by electron degeneracy. Electrons are packed so densely that quantum exclusion provides resistance to further compression. Temperature plays only a minor role in maintaining equilibrium. In neutron stars, the situation is even more extreme. Pressure is supplied primarily by degenerate neutrons, with additional contributions from nuclear interactions, whose detailed behavior remains uncertain. The stiffness or softness of these equations of state directly controls how the star deforms under tidal stress. When a white dwarf or neutron star experiences a tidal field, the initial response is elastic. The star's shape distorts slightly, developing a tidal bulge aligned with the perturbing companion. For weak tides, this deformation remains small and reversible. As tidal stress increases, however, the internal response becomes nonlinear. In neutron stars, the solid crust plays a critical role at this stage. Beneath a thin atmosphere lies a rigid lattice of nuclei embedded in a sea of degenerate electrons. This crust can support shear stress up to a finite breaking strain. As tidal forces grow, shear stress builds in the crust. When it exceeds the breaking threshold, the crust fractures. These crustal failures are known as starquakes. Unlike earthquakes on Earth, starquakes involve the sudden rearrangement of matter under immense pressure, releasing energy stored in elastic strain. The cracking of the crust can trigger seismic oscillations that propagate through the star, coupling mechanical deformation to internal modes of vibration. Starquakes are not merely mechanical curiosities. They can alter the star's rotation, magnetic field configuration, and thermal state. In magnetized neutron stars, crustal fractures may rearrange magnetic field lines anchored in the crust, releasing electromagnetic energy. Even in weakly magnetized stars, starquakes can excite global oscillation modes that interact with tidal forces in complex ways. In close binaries containing neutron stars or white dwarfs, tidal forces evolve dynamically as the objects spiral inward. in spiral is driven primarily by gravitational wave emission, which removes orbital energy and angular momentum. As the separation decreases, tidal coupling strengthens. The tidal field varies periodically at the orbital frequency, and if this frequency approaches the natural frequencies of the star's internal modes, resonant excitation can occur. Tidal resonances arise when the orbital motion efficiently transfers energy into specific oscillation modes of the star. These modes can include fundamental fluid modes, shear modes in the crust, and gravity modes associated with buoyancy and stratified layers. Resonant excitation amplifies deformation beyond what would occur under static tides alone. Even a relatively weak tidal field can produce a strong response if it remains in resonance long enough. Mode excitation has two key consequences. First, it increases internal heating. Energy deposited into oscillations is eventually dissipated through damping mechanisms, converting mechanical energy into heat. Second, it modifies the orbital evolution. Energy and angular momentum transferred into stellar modes are temporarily removed from the orbit, altering the in-spiral rate. These effects are subtle but measurable in principle. Damping plays a critical role in determining how resonances evolve. In white dwarfs, damping may occur through viscosity, radiative diffusion, or nonlinear mode coupling. In neutron stars, additional mechanisms come into play, including superfluid mutual friction, neutrino emission, and viscous dissipation in the core. The efficiency of damping determines whether resonances produce sharp, transient effects, or broader, smoother modifications to the in-spiral. The interplay between tidal excitation and damping leaves imprints on the gravitational wave signal emitted by the binary. Gravitational waves encode the phase evolution of the orbit with extraordinary precision. Any process that alters the in-spiral rate, even slightly, changes the accumulated phase. Tidal deformation increases the effective moment of inertia of the stars and modifies the gravitational potential, introducing phase shifts relative to the point mass approximation. These tidal phase imprints carry information about the internal structure of neutron stars and white dwarfs. In neutron star binaries, the magnitude of tidal deformability depends sensitively on the equation of state. A stiff equation of state produces larger stars that deform more easily, leading to stronger tidal effects and larger phase shifts. A soft equation of state produces more compact stars with weaker tidal signatures. Measuring these imprints allows constraints on the physics of ultra-dense matter. Resonant effects can produce additional, localized features in the gravitational wave phase. If a mode is strongly excited, the in-spiral may briefly accelerate or decelerate relative to the smooth evolution expected from point masses. Detecting such features requires high signal-to-noise observations and careful modeling, but they offer a unique probe of stellar interiors that cannot be accessed by electromagnetic observations alone. As in-spiral proceeds toward merger, tidal forces can become strong enough to cause mass shedding. In white dwarfs, tidal stripping may begin well before contact. Material can be pulled off the outer layers and form a stream flowing toward the companion. This mass transfer alters the mass ratio and angular momentum distribution, potentially stabilizing or destabilizing the system, depending on circumstances. In neutron stars, pre-merger mass shedding is more constrained because of the star's compactness and strong gravity. However, for sufficiently unequal mass binaries or rapidly rotating stars, tidal forces can strip material from the outer layers shortly before merger. This ejected matter may form an accretion disk or tidal tails, contributing to electromagnetic counterparts such as short gamma-ray bursts or kilonova emission. The onset of mass shedding marks a transition from linear tidal response to fully nonlinear dynamics. Once material is removed from the star, the equation of state governing the remaining core changes, and the system's evolution becomes highly sensitive to microphysical details. Hydrodynamical simulations are required to capture this regime, and uncertainties in the equation of state propagate into uncertainties in predicted observables. Throughout these processes, the extreme nature of the matter involved shapes the outcome. Degenerate pressure resists compression but offers little resistance to shear once breaking thresholds are exceeded. Nuclear forces provide enormous binding at small scales but do not prevent large-scale deformation. Tidal forces exploit these properties, channeling orbital energy into internal modes, heat, and mass loss. What distinguishes tidal interactions in neutron stars and white dwarfs from those in ordinary stars is the coupling between gravity and microphysics. The response is not governed solely by bulk fluid dynamics, but by quantum mechanical principles embedded in the equation of state. Tidal deformation becomes a probe of fundamental physics, revealing how matter behaves when squeezed to densities far beyond terrestrial experience. These systems also demonstrate that tidal forces are not merely destructive precursors to merger. They actively shape the merger itself. By altering spin, internal structure, and mass distribution prior to contact, tides influence the geometry, energetics, and observable signatures of the final collision. Gravitational waves carry this information across cosmic distances, allowing distant observers to infer the internal constitution of objects that cannot be reproduced or directly sampled. In neutron stars and white dwarfs, tidal forces therefore serve a dual role. They threaten structural integrity while simultaneously encoding deep physical information. Crustal cracking, resonant oscillations, and pre-merger mass shedding are not isolated phenomena. They are interconnected expressions of how extreme matter responds to differential gravity. Through them, tides transform compact objects from passive participants in binary motion into active, responsive systems whose internal physics shapes what the universe ultimately reveals. Spaghettification is often framed as a uniquely black hole phenomenon, but this association is more cultural than physical. The defining mechanism behind spaghettification is not the presence of an event horizon, nor extreme gravity in an absolute sense, but differential gravity acting across an extended object. Wherever tidal gradients become large compared to an object's internal binding forces, the same sequence of stretching, compression, heating, and structural failure can occur. Black holes provide one extreme environment where this happens, but they are far from the only one. In many astrophysical systems, tidal destruction unfolds in full view, without horizons, singularities, or relativistic complications. A natural starting point is stellar binaries, particularly those in which one star fills or overfills its Roche lobe. In a close binary system, each star resides within a region of space where its gravity dominates. The boundary between these regions defines the Roche lobes. As stars evolve, their radii change. When one star expands enough to reach its Roche lobe, matter at its surface becomes gravitationally unbound with respect to the star and can flow toward its companion. Roche lobe overflow is a controlled, long-duration form of tidal stripping. The star is not destroyed instantly, but its outer layers are stretched toward the companion along the line connecting the two stars. Material flows through the inner Lagrange point, forming a narrow stream. This stream is the stellar analogue of spaghettification. Matter is elongated, thinned, and guided by differential gravity rather than by explosive forces. The geometry of this flow mirrors the same tidal tensor structure discussed earlier. Stretching dominates along the binary axis, while compression and shear shape the stream's cross-section. Over time, continued mass loss can dramatically alter the donor star's structure. In extreme cases, the star is reduced to a stripped core or destroyed entirely. No black hole is required. Only sustained tidal gradients exceeding the star's self-gravity in its outer layers. Close encounters with neutron stars provide a more violent variant. Neutron stars possess intense gravitational fields and extremely steep tidal gradients near their surfaces. A normal star or white dwarf passing sufficiently close to a neutron star can experience severe tidal deformation long before any physical contact occurs. stretching begins well outside the neutron star's surface, drawing matter into elongated filaments and tidal tails. In such encounters, the timescale is short and the deformation rapid. Axial stretching and transverse compression act together, producing shocks and heating. If the encounter is deep enough, the disrupted object can be drawn into a long, thin stream that wraps around the neutron star or escapes entirely. This is spaghettification in every physical sense. Anisotropic tidal strain driving elongation, thinning, and loss of coherence. Yet there is no horizon, no singularity, and no relativistic point of no return. Planetary systems provide even more familiar examples. Large moons and planets experience tidal stretching whenever they pass close to a more massive body. Under ordinary conditions, these tides are gentle, producing modest bulges and heating. Under extreme conditions, they become destructive. When a planet or moon approaches within its Roche limit, tidal forces exceed self-gravity, and structural failure begins. The deformation follows the same pattern seen in more extreme systems. The object elongates along the radial direction, flattens laterally, and begins to shed material. This material is drawn into streams and arcs that trace the object's former orbit. Given sufficient time, the original body is completely dispersed into a ring or debris disk. This process is mechanically indistinguishable from spaghettification near a black hole, differing only in scale and outcome. A historically well-documented case is the breakup of comet Shoemaker-Levy 9 during its encounter with Jupiter. As the comet passed within Jupiter's Roche limit, it was stretched into a chain of fragments. The gravitational field of Jupiter imposed strong differential acceleration across the comet's length. The nucleus, already a loosely bound aggregate, could not withstand the stress. It fractured into multiple pieces aligned along its orbit, producing the characteristic string of pearls appearance observed from Earth. Shoemaker-Levy 9 demonstrates every essential element of spaghettification. Differential gravity elongated the object. Transverse compression and shear weakened internal cohesion. Structural failure occurred along preferred axes determined by the tidal field. The resulting debris followed independent trajectories dictated by the energy gradient imposed during disruption. No exotic physics was involved. The process unfolded entirely within Newtonian gravity. Planetary tidal stretching also occurs during close stellar flybys, informing planetary systems and in densely packed exoplanetary environments. Hot Jupiters experience continuous tidal deformation that can inflate their atmospheres and strip mass over time. In more extreme cases, planets on highly eccentric orbits can be partially or fully disrupted during periastron passages, leaving behind streams of gas or remnant cores. These examples illustrate a critical point. Black holes are not unique in their ability to spaghettify matter. They are efficient at it because they combine large masses with compact sizes, producing strong tidal gradients over short distances. But the underlying physics, differential gravity acting across an object, is universal. What changes across systems is not the mechanism, but the scale. In binaries, the process may take millions of years. In planetary encounters, it may take hours or days. Near neutron stars, it may take seconds. Near stellar mass black holes, milliseconds. The same equations apply in every case. The same tidal tensor governs deformation. The same balance between external gradients and internal cohesion determines outcome. This universality is why tidal destruction appears across astrophysics in so many guises. Stellar streams in galaxies, rings around planets, accretion disks in binaries, debris tails from disrupted stars, and fragmented comets. Each is an imprint of spaghettification operating in a different regime. It also explains why invoking black holes exclusively can obscure understanding. The dramatic imagery associated with horizons and singularities distracts from the deeper principle. Tidal destruction does not require relativistic gravity. It does not require horizons. It does not require infinite curvature. It requires only that the gradient of the gravitational field across an object exceed the object's ability to hold itself together. In this sense, spaghettification is not a special effect reserved for extreme space-time. It is a limiting case of a process that operates everywhere gravity acts on extended matter. The same differential pull that raises Earth's tides, locks moons, strips stars and shreds comets can, under sufficient intensity, reduce any object to elongated debris. Recognizing this continuity strips spaghettification of its mystique while expanding its relevance. It is not an exotic endpoint of gravity, but one of its most basic consequences when scale and proximity align unfavorably. Black holes make this outcome unavoidable and rapid, but they do not invent it. They merely sit at one extreme of a spectrum governed by universal tidal physics. Spaghettification, then, is not defined by where it happens, but by how gravity acts. Wherever differential acceleration overwhelms cohesion, structure fails in the same anisotropic way. This universality is what makes tidal destruction such a powerful organizing principle across astrophysics, linking phenomena from shattered comets to disrupted stars under a single, scale-independent framework. Tidal destruction is not only a theoretical construct inferred from equations and simulations. It leaves clear, testable imprints in astronomical data. Because tidal disruption reshapes matter in highly organized yet extreme ways, it produces observational signatures that differ systematically from those of supernovae, steady accretion, or ordinary stellar variability. Over the past decades, these signatures have matured into a diagnostic toolkit that allows astronomers to identify tidal events, reconstruct their geometry, and infer the physical conditions under which spaghettification occurred. One of the most distinctive observational features of tidal disruption events is the temporal behavior of their luminosity. After a star is disrupted, the bound debris returns to the vicinity of the compact object at a rate determined by the energy distribution imparted during the tidal encounter. As discussed earlier, this distribution is approximately flat in specific orbital energy. This leads to a characteristic fallback rate that declines as a power law in time, proportional to time raised to the negative 5/3 power. This power law decay appears directly in observed light curves. After an initial rise to peak brightness, many tidal disruption candidates exhibit a smooth, long-term decline consistent with this scaling. The persistence of this decay over months to years distinguishes tidal events from supernovae, whose luminosity is governed by radioactive decay chains and radiative diffusion through expanding ejecta. The power law behavior is not merely a fitting convenience, it is a direct consequence of tidal physics and orbital mechanics, linking observed brightness to the debris dynamics set at the moment of spaghettification. Deviations from the idealized power law are themselves informative. Early time departures can indicate inefficient circularization or obscuration by outflows. Late time deviations may signal transitions between accretion regimes or the exhaustion of bound debris. By modeling these deviations, astronomers can infer the efficiency of energy dissipation, the geometry of the debris streams, and the presence of winds or jets. Spectroscopy provides an additional window into tidal destruction. As stellar debris is stretched into long, thin streams, it acquires a wide range of velocities. Portions of the stream move toward the observer, while others recede, producing Doppler-broadened spectral lines. In many tidal disruption events, hydrogen and helium emission lines are observed with widths corresponding to velocities of tens of thousands of kilometers per second. These line widths are far broader than those produced by ordinary stellar atmospheres or galactic gas clouds. The shape of these lines carries geometric information. Asymmetric line profiles can indicate preferential viewing angles or obscuration. Double-peaked lines may arise from rotating or precessing debris disks. time evolution of line widths and centroids traces the changing kinematics of the debris as it circularizes and accretes. In this way, spectral line broadening acts as a direct diagnostic of the spaghettified debris streams. The wavelength at which a tidal disruption event is most luminous depends strongly on the black hole mass and the structure of the accretion flow. Events involving lower mass black holes tend to produce hotter accretion disks, with emission peaking in the ultraviolet or soft X-ray bands. Higher mass black holes produce cooler disks, whose emission shifts toward optical wavelengths. As a result, tidal events span a broad spectral range, from X-ray bright flares to optically selected transients. X-ray tidal events often show rapid variability and high peak temperatures, reflecting compact, efficient accretion near the black hole. Optical tidal events tend to be longer-lived and may be dominated by reprocessed radiation from debris streams or outflows rather than direct disk emission. The coexistence of X-ray and optical populations was initially puzzling, but is now understood as a natural outcome of how tidal debris interacts with its environment. The relative strengths of X-ray and optical emission provide insight into the geometry of the system. Strong X-ray emission suggests that the inner accretion flow is directly visible, while weak or absent X-rays imply obscuration or inefficient circularization. Monitoring how emission shifts between bands over time reveals how the system evolves from debris fallback to disk-dominated accretion. Polarization measurements offer a more subtle but powerful diagnostic. Light emitted or scattered by asymmetric structures becomes polarized. In tidal disruption events, the debris geometry is highly anisotropic. Elongated streams, warped disks, and bipolar outflows can all imprint polarization signatures on the observed radiation. Detecting polarization and tracking how it changes with time and wavelength provides constraints on the three-dimensional structure of the emitting and scattering regions. Although polarization signals are typically weak, they are invaluable because they break degeneracies that cannot be resolved by photometry or spectroscopy alone. For example, polarization angles can reveal the orientation of debris streams or disks relative to the observer. Changes in polarization over time can indicate precession or the emergence of new structural components as the event evolves. Relativistic effects introduce additional observational signatures that are unique to tidal disruption near compact objects. One such effect is relativistic apsidal precession. As debris streams orbit the black hole, their pericenters advance due to space-time curvature. This precession alters where returning streams intersect and shock, influencing disk formation and emission. In some events, quasi-periodic modulations or evolving spectral features have been interpreted as evidence of precessing debris or disks. The detection of such signatures provides a direct probe of strong field gravity. The amount of precession depends on the black hole's mass and spin, offering a way to infer these parameters from tidal events in otherwise dormant galactic nuclei. The ability to detect and interpret these signals depends critically on event rates. Tidal disruption events are rare on a per-galaxy basis, with typical rates estimated at roughly one event per 10,000 to 100,000 years per galaxy. However, because the observable universe contains billions of galaxies, ongoing surveys detect multiple events each year. Event rates vary with galactic properties. Dense nuclear star clusters and galaxies with certain stellar distributions are more efficient at feeding stars into lost cone orbits. Observed rates therefore provide information not only about black holes, but about the dynamical state of galactic centers. Comparisons between observed rates and theoretical predictions test models of stellar dynamics, relaxation processes, and black hole demographics. Selection effects play a major role. X-ray surveys preferentially detect events around lower mass black holes, while optical surveys favor higher mass systems or those with efficient reprocessing. Accounting for these biases is essential when extrapolating observed rates to intrinsic rates. Discrepancies between predicted and observed rates continue to motivate refinements in both theory and observation. Taken together, these diagnostics form a coherent picture. Light curve decay reveals the fallback physics set by tidal energy redistribution. Spectral broadening maps the kinematics of spaghettified debris. Wavelength dependence distinguishes accretion regimes. Polarization encodes geometry. Relativistic signatures probe strong gravity. Event rates connect individual events to galactic-scale dynamics. What makes tidal disruption events particularly valuable is that they illuminate otherwise invisible black holes. Many galactic nuclei are quiescent, showing little or no accretion activity. A tidal event briefly turns such a nucleus into a beacon, allowing measurement of black hole mass, spin, and environment. In this sense, spaghettification acts as a natural experiment conducted by gravity itself. Observational evidence thus closes the loop between theory and reality. The same tidal physics that predicts stretching, compression, and energy redistribution also predicts how light should behave when matter is torn apart. The agreement between these predictions and observed phenomena confirms that spaghettification is not a speculative idea, but a physically realized process shaping what astronomers see across the universe. Tidal forces do not merely destroy. Over cosmic timescales, they sculpt. They redistribute matter, energy, and angular momentum in ways that leave persistent, observable structures long after the original encounter has ended. When viewed across enough scales and epochs, tides emerge as one of the universe's primary organizing agents, shaping everything from stellar orbits to galactic morphology. Their importance lies not in rare catastrophic events alone, but in their cumulative, irreversible influence on structure. One of the clearest large-scale manifestations of tidal sculpting is the formation of stellar streams and shells. When a smaller galaxy or star cluster orbits a more massive host, differential gravity acts across its extent. Stars on the near side experience a stronger gravitational pull than those on the far side. Over time, this gradient strips stars from the satellite system. The stripped stars do not disperse randomly. They retain memory of their original orbital energy and angular momentum, forming elongated streams that trace the satellite's orbit through the host galaxy's halo. These stellar streams can persist for billions of years. They wrap around galaxies in thin, coherent filaments, gradually phase-mixing but often remaining detectable long after the progenitor system has been fully disrupted. Shell structures arise in a related way, particularly during radial mergers. As debris oscillates in the host galaxy's potential, stars pile up near orbital turning points, creating sharp-edged shells that appear as faint arcs in galactic halos. Both streams and shells are fossil records of past tidal interactions, encoding information about gravitational potentials and merger histories. At larger scales, tidal stripping operates throughout galaxy clusters. As galaxies fall into a cluster environment, they encounter the cluster's deep, extended gravitational potential, as well as repeated close encounters with other member galaxies. Tidal forces remove stars, gas, and dark matter from galactic outskirts. Over time, this process truncates galaxies, suppresses star formation, and populates the cluster with diffuse intracluster light composed of stars no longer bound to any single galaxy. This stripping is not symmetric. Low-mass galaxies are affected first and most severely, while massive galaxies retain their cores longer. The cumulative effect reshapes the galaxy population within clusters, producing systematic trends in morphology and stellar content. Spiral galaxies lose gas and fade into lenticular or elliptical systems. Tidal forces, acting repeatedly and persistently, drive environmental evolution without requiring violent collisions or explosions. Warped disks provide another example of tidal sculpting in action. Galactic disks are often observed to bend or twist at large radii, deviating from a single flat plane. These warps arise when tidal torques act on the disk from misaligned gravitational sources, such as satellite galaxies, asymmetric dark matter halos, or ongoing accretion from the cosmic web. Because the outer parts of disks are weakly bound, they respond more readily to such torques. The shape and orientation of a warp encode information about the surrounding gravitational field. By modelling disk warps, astronomers can infer the shape and orientation of galactic halos, including their dark matter components. In this way, tidal forces turn disks into sensitive probes of invisible structure. The warp is not a defect or anomaly. It is a dynamical response to external tidal influence. Over long timescales, tides also redistribute angular momentum throughout astrophysical systems. In binary stars, tidal torques synchronize rotations and circularize orbits. In planetary systems, tides slow rotation, lock moons, and migrate orbits. In galaxies, tidal interactions during mergers and flybys transfer angular momentum from baryonic components to dark matter halos and outer regions. This redistribution is irreversible and cumulative. Angular momentum transport is closely tied to energy dissipation. Tidal deformation converts ordered orbital or rotational motion into internal heat and random motion. This conversion increases entropy. In this sense, tidal forces act as entropy generators. They drive systems toward more mixed, less ordered states. Orbits become randomized, structures become smoother, and sharp features are erased over time, unless continually replenished. This entropy production is not a metaphorical statement. It has a precise physical meaning. Tidal interactions dissipate mechanical energy through friction, shocks, and dynamical heating. They populate phase space more uniformly, reducing the ability to reconstruct initial conditions. The universe's large-scale trend toward increasing entropy is expressed locally through tides that grind down coherent structures into diffuse distributions. The role of tides as entropy generators explains why certain structures are transient while others are persistent. Thin stellar streams eventually dissolve into smooth halos. Compact groups disperse. Disks heat and thicken. These outcomes are not failures of structure formation, but expected consequences of tidal evolution acting over billions of years. Perhaps the most powerful aspect of tidal sculpting is that it reveals invisible mass. Tidal effects depend on the gravitational field, not on luminous matter alone. When stars are stripped into streams, their trajectories trace the total gravitational potential they move through. Deviations from simple orbits reveal the presence, distribution, and shape of dark matter. Warps, shells, and intracluster light all respond to mass that cannot be seen directly. Because tidal structures are sensitive to gravitational gradients, they are especially effective at probing extended diffuse components like dark matter halos. The detailed morphology of a stellar stream can distinguish between smooth and clumpy halos, constrain halo flattening, and even reveal perturbations from unseen substructures. In this way, tides act as natural detectors, amplifying the gravitational influence of otherwise invisible mass. This diagnostic power extends across scales. In planetary systems, tides reveal internal structure through orbital evolution and heating. In stars, tides expose equations of state. In galaxies, tides map dark matter. The same underlying physics applies in each case. Differential gravity couples visible matter to the total mass distribution, making tides a universal translator between what can be seen and what cannot. Taken together, these effects justify describing tidal forces as a universal sculptor. They carve streams from galaxies, rings from moons, disks from debris, and halos from disrupted systems. They erase some structures while creating others. They drive irreversible evolution toward higher entropy states, while preserving long-lived signatures of past interactions. Unlike explosive processes, tides operate continuously. They require no special triggers beyond gravity itself. Wherever extended objects orbit within non-uniform gravitational fields, tides are at work. Over sufficient time, their influence becomes dominant, reshaping systems in ways that are subtle in the short term but profound in the long term. In this sense, spaghettification is only the most dramatic expression of a much broader principle. It represents the endpoint of tidal sculpting, when gradients become extreme and timescales short. The same mechanism, operating more gently, builds the large-scale architecture of the universe, from faint stellar streams to warped galactic disks, from stripped cluster galaxies to the quiet redistribution of angular momentum. Tides leave an imprint that accumulates rather than fades. Tidal forces therefore occupy a unique position in astrophysics. They are neither rare catastrophes nor gentle background effects. They are persistent, scale-independent agents of transformation. By studying the structures they create and the entropy they generate, it becomes possible to read the gravitational history of systems across cosmic time and to infer the presence of mass that cannot be seen directly. In the end, tides remind us that gravity's most important role is not simply to bind matter together or pull it inward. It is to differentiate, to redistribute, and to sculpt. Through tidal forces, gravity writes its signature into the shape, motion, and fate of matter throughout the universe.